A short presentation by Professor Rajiv Ranjan. Professor Rajiv Ranjan, of course, he is a professor of the department, but he's also the chair, current chair of the department. And his work, बताइएगा, ठीक है. So he will have a short talk, mainly towards application of XRD and SEM and how can we, solve a rather complicated problem using these techniques.
Give a item number.
You are being recorded.
Okay.
So it will be a good item.
And Professor Praveen Kumar, who is the sole karta dharta of this program, said that let us have some chaupal. So in that context, I have been suddenly roped in. My problem was that I wanted to have some tea or coffee, and it was being served freely here, and they just cornered me that you can't take so freely, and then better do something. So what I will do is I'll give you some case studies where I've used normal XRD, normal SEM to solve some interesting puzzle, right? So just to sensitize you that this is, most people use X-ray and SEM as a kind of, when you are writing a paper, you just want a photo to be pasted in your paper, a kind of something to fill in the space, and at the most you say, okay, this is the grain size, this is the phase, XRD, there is no impurity peaks, so I have prepared the single phase and so on, right. Most of you generally limit your use of XRD to these trivial things. Personally, I go beyond this, because trivial things are already there, but there are some hidden information which XRD carries and which tells you a lot about fundamental science aspect of the material. I will just try to give you a feeling that how you can, if you know the basics very well, if you know how your equipment works, for example, then you can design experiments. Within the same setup, you can get very, very interesting data, kind of data. Okay, you have heard, you have been lectured about XRD. ये काम नहीं कर रहा है क्या? AC? Room is getting warm. So you have been told about XRD, right? Okay. And you have seen the XRD machine? Not yet. Okay. So you have a X-ray, right? You have a sample and you have a detector. These are the three things. Now, though I think people will teach you about X-ray diffraction in a very, very simple manner, but the equipments which you have, most of the equipment which is there in the lab, they work on a slightly complicated principle than what is shown in the diagram. In the diagram you have, I need to write, can I? For example, you have a sample here, you have an X-ray beam coming, right? And you have a diffracted beam at different 2 theta values, right? This is the direct beam, this is 2 theta 1, 2 theta 2 and so on, right? You have a diffracted beam. Generally, in the textbooks you see such diagrams, right, where the X-ray is penetrating your specimen and you have a diffracted beam. That is called Debye-Scherrer geometry. Generally, though it is shown in the textbook, but that is not the kind of equipment we see in the laboratory. They work on a slightly different principle. I don't know whether they are taught all this, perhaps not. They work on something called Bragg-Brentano reflection geometry. This is transmission geometry, which you find in every textbook, solid state physics or any metallurgy textbook. But what is not talked about, and which is the work instrument, the kind of instrument we use, right, which is available, that is reflection geometry, in which you have a powder or polycrystalline specimen like this. So, when you have a diagram like this, basically this represents parallel X-ray beam, right, which is bathing the sample. And when you write when you show a diagram like this, basically they are parallel beams in this direction which your detector is recording, right. It is not one line, right. One line represents a set of parallel X-ray beam. Your X-ray beam has a cross section, right, in which every beam is parallel to each other. So, this is shown in the book, but generally what you see, the equipment we use is called Bragg-Brentano. I could have talked about it, but I will not talk about, I will just make you curious, you read yourself or ask the teacher who is teaching XRD. So, here you do not have a parallel beam, you have a solid sample like this, right, and you have a divergent beam which is falling on the sample, which is very different from this. Here is a parallel beam falling on the sample, here is a divergent beam falling on the sample, and from the samples, this is a polycrystalline specimen, the beams are diffracted and they are focused, which is very different here. There is nothing like focusing, right. A parallel beam falls on the sample specimen diffract the X-ray, and a parallel beam in some direction goes, you collect that, that is the 2 theta value. So, this is called Debye-Scherrer geometry. This is Debye-Scherrer geometry of diffraction, and this is called Bragg-Brentano reflection geometry. Unfortunately, the textbook does not show this picture, but this is what you use. Okay. So, during my PhD days, of course, I was not taught about all this, but I was handling the XRD machine, and I used to read the manual of this machine which works on this principle. So, I taught myself what it does. Okay. So, this understanding helped, when I came here as a faculty, helped me design new experiments, okay, which would not be possible if I had not known the working principle of this machine. So, for example, when you are, this is a reflection geometry, right, here the specimen can be any thick, all the diffraction is happening from the thin region from the sample, right, and then you have, so your specimen, here your specimen thickness is a problem, because X-ray cannot penetrate what distance, any idea? Micron size, maybe tens of 20s of micron at the most, right. Higher the Z, less is the penetration value, right. So, here you do not have that problem. So, you do not have to make a very thin sample, because the reflection geometry, your surface is already available, your X-ray is coming and the diffracted beam is there on the surface. So, you do not worry about how thick or thin your sample is, right. At the same time, if you look at the geometry, you know Bragg's law. Bragg's law, you are very familiar with this diagram, is not it? What are these representing? Planes. This is HKL plane, right, and what is this is the DHKL, right, and this is the theta, this is normal to the plane, this is normal. If you look, for example, this diagram and this diagram looks very similar, but they are different, but at the same time there is similarity. For example, if you look at the central beam, forget about this central beam, this is like this diagram, right, among this divergent beam. If you look at the central beam, it is very common to this diagram, but this is experiment, this is your schematic of Bragg diffraction, correct. Now, what does it mean? It means that if this is the case, those grains whose HKL planes is parallel to this surface, now this is the surface of the specimen, right, this is what, no specimen, this is HKL plane, but this is specimen, right, and this geometry is similar to this. What does it mean? Those grains on the surface whose HKL is what, parallel to the surface, are satisfying Bragg's law, right. Those HKL grains, those HKL which is not parallel to the surface will not be satisfying the law. because a polycrystalline you have HKL in all possible directions, right. Okay. So, once you understand this principle, what the experiment I do here is, for example, now this is a very easy for me. I can apply it. I work on ceramics, mostly called piezo ceramics, which are insulators, and they do very interesting stuff when I apply electric field. They change sometimes crystal structure, they change sometimes the domains, orientation, all these things happen, and I can capture it with my normal XRD. Fortunately, it works. It is working in this geometry, and it gives me that advantage. So, I design an experiment where I apply electric field to this ferroelectric insulating material, and as a function of field I can see what are the changes in the diffraction pattern. I can understand phase transformation as a function of electric field and so on, right. So, this understanding, this experiment everybody have in India, many places you have such a diffractometer, but I could design this experiment because I knew the mechanism of how this instrument is working. I can't design this experiment on this geometry. I will have some data, but that data I can't interpret. It will have no value. So, understanding of the working principle of the machine is also very important, apart from the schematic basics, right. Because if you understand the working principle of the machine, you can design experiments, and once you have your designing capability, it can generate lots of valuable data which is uncommon, right. Suddenly your science quality increases with the same material. All right. That is one aspect I want to highlight, that do not treat XRD as a very where you get a photo and you get a single phase and you are done with. If you are working on functional materials, for example, you can do a lot. I will just take an example of barium titanate. How many people know barium titanate? Have you heard about? Okay, it is a very simple structure, perovskite structure. The structure is very simple. You have barium at the corners. If I don't know if I have a photo of this. Here it is. It's a very famous material, piezoelectric material, where at the corner you have barium, at the faces of this unit cell you have oxygen, and titanium is at the body center. Very simple structure. Okay. It's a piezoelectric material discovered during the World War II. Now, this is a tetragonal structure, is well known, it is documented in book, it is a tetragonal structure. Barium titanate is tetragonal ferroelectric phase. Okay. Now, if you look at the normal XRD, etc., I will not go into it. This is normal XRD. It shows peak splitting, which yesterday I think somebody was talking about, peak splitting, Sanjay was talking about, right. And you get the tetragonal phase, tetragonal structure verified, no problem. But we had something in our mind which perhaps were making us uncomfortable, that it should not be tetragonal, but we had no way to verify that it cannot be tetragonal. The normal XRD resolution was not able to tell me anything beyond tetragonal description. Okay. So, this is a very good example of how synchrotron can tell you more information. Yesterday Sanjay was talking about, and this is a case where barium titanate, such old material, right, is a classic ferroelectric material, such old material, we discovered something very interesting. This is a synchrotron data collected from European synchrotron radiation facility in France, okay, for barium titanate. You look, this is the entire 2 theta range. I did not worry about these strong peaks here. I rather focus on this part of this data, synchrotron data. If you look at the whole scale, right, as if there is nothing here, right. So, I focused on that part of the data and I zoomed it vertically. Now, the beauty of this data is, even at such small intensity, relative intensity, where it is almost 0, when you zoom it, it looks something so nice. The fluctuation in the data is not there. It means that whatever the shape of the peaks you get, you are very sure about it. It is not scattered data like zigzag, because once you have a small intensity, there is a lot of scatter in the data. You cannot say that what the shape is, etc. Right? Now, when I zoom it, even at such large Q value, you get such well defined peaks. Now, this is the background, this is a noise or background, and this is the signal, right. So, very good signal to noise ratio. So, if you have data of very good signal to noise ratio, then what it tells me is that what I am going to highlight. Now, I have taken one of those peaks from high angle, separated here. Now, all these peaks which I have plotted here are supposed to be one peak, singlet. Okay? If it is tetragonal, they should be all singlet. One peak, only one peak, symmetric peak. But I found, you can see there is asymmetry. For example, this not looks like a singlet, right? There is overlap of more than one peak. When you see such a data, you may say that okay, it can be fluctuation, right? I was also having that doubt. So, what I asked my collaborator who collected the data, can you please repeat it? You should always doubt your data. You should be the first person to doubt your data, right, and ask question about the quality of data you get. And then I said that I have got something interesting. This peak should have been singlet, but I am getting something non-singlet. Can it be a fluctuation in the data statistics? The person repeated the experiment and he exactly reproduced what I had it before. So, when you reproduce something, then it cannot be, randomness cannot be reproduced, right. So, that gave us a confidence. This led us to understand that the crystal structure of barium titanate is not really tetragonal. It has slight distortion from tetragonal, and we proved that it is a monoclinic. So, XRD data can't tell you. Symptoms were there in the XRD data, which made us believe that there is something. For example, that symptom, for example, when we do, there is extra intensity when I am trying to fit the raw data with the tetragonal fit, I got extra intensity. So, these were the symptoms, but not very clear enough, and those extra intensity we could clarify when we understand synchrotron, that oh, this at the local scale you have monoclinic distortion, not tetragonal. This understanding helped us to understand the property of barium titanate much more better way. Okay? And we published this. If you do such good analysis with simple material, well known material, also you can publish in a good journal. We published this, just the structure of barium titanate in Physical Review B in 2015. This is just XRD. I will just maybe 5 minutes where I will tell you about, I will not talk about this. We have done so many things with simple XRD, solved many problems. Okay? These are some examples, but I will just touch upon something interesting where SEM is also playing a role. I come from a physics background. How many of you are from physics background? Lot many. Okay? So, in physics, with people with physics background, XRD is the main thing, right? And hardly we care about SEM. I had the same mindset. Now, I was working on a material alloy system like bismuth ferrite and lead titanate mixed together, and they form a solid solution. So, it is not two phase, they form one single phase. So, there is certain compositions where which is of interest called morphotropic, which is a phase boundary in the phase diagram, right. So, and these such compositions where two phases can be coexisting, they are very interesting from the piezoelectric point of view, right. So, just an idea. So, many people have been working on this material, and this phase coexistence range was reported very widely by different people for the same material. For example, X is, for example, I think X is what here, maybe bismuth ferrite, one of these is X, here is X, lead titanate is X, right. So, different people have reported different composition of X where the two phases coexist, very wide range, 27 to 34, somebody is very narrow, you see 20 to 40 even, such a huge range in which two phases coexist. The question is, what is the problem? Are they making random samples, bad quality samples? How to solve this puzzle? We were also puzzled about it because we were working on this material. We found something very interesting. When these are ceramics, oxides, right? So, we have to make them, mix them, heat at high temperature to densify. We were finding that on different occasions, the same material were behaving different, the sintering behavior was very different. Sometime it would become powder, everything fixed, time fixed, so temperature all fixed and so on. Sometime it will remain as a pellet, dense pellet, sometime it behave like this, okay. And so very random behavior, sintering behavior, which was not very common, very, so we were scratching our head what is happening. And when you get this thing, the structure was tetragonal. When you do the XRD of this powder, the structure was tetragonal. When you do the structure of this powder, it is a tetragonal plus rhombohedral, right, and so on. So, it is a very erratic phase behavior this material was showing, very, we spent months to understand what is it, that why it is showing sometime tetragonal, sometime rhombohedral, sometime mixed phases and so on. It was very erratic. We didn't experience this behavior with other materials, right. The student was thinking that she was making a lot of mistakes. What we found was the answer came from the SEM understanding. So, I told her, hey, just casually, because we were trying to understand why different time difference, it was showing different sintering behavior in different phases. I told her casually, why don't you do SEM? It is freely available in the department. So, all out of frustration, because we are searching for origin, that why it should. She did the SEM and it was very surprising. We found that when after sintering it was broken into powder, the grains of the powders were very big like this, separated grains, SEM, approximately 10 to 20 micron, and they were fragmented. And this was showing a tetragonal structure. When the pellet was not broken into pieces, it survived the sintering. The XRD pattern looked like this, and you see the grain size is very small. So, we found that there is a very strong correlation between the grain size and the phase the material is forming, okay. So, this was a very first observation which led us to think that there is a correlation between grain size and the phase. And I will just summarize. What has been observed? This was observed. Experiment done at different time, one composition, select one composition. Sometime after sintering, you get this. You just remove the, you see partly broken, partly pellet, partly broken, powder automatically. Sometime you get the whole pellet. Sometime you get the complete material broken to powder. This is the observation with the eyes, right. Then we had to do systematic experiment. We said, okay, let us do the XRD of this one, okay, and we found that it is showing rhombohedral phase. When we did the XRD of completely broken powder, it shows only tetragonal phase, and when we had this combination, we had both rhombohedral and so on. So, even the phase fractions were very much different time to time. So, there was very inconsistency in what we observed. To find out what is that inconsistency, is there any science behind that inconsistency, was the real puzzle to explain that, right. So, what I am saying is, we found that answer in the SC, when we did the SEM of the different powders, different materials, we found that the one which was broken has a very large grain size, and it was a tetragonal, and this was consistency. Whenever we get that powder which was broken, it always showed the tetragonal structure, and whenever we had this scenario, the pellet survived the sintering, it showed this two-phase coexistence, rhombohedral plus tetragonal two-phase coexistence. So, this was, at least we are sure about. This is a microstructural correlation between what we see and the fragment and the sintering behavior. Got it? Now, the question is the grain size playing a role? Looks like a grain size playing a role. So, what kind of experiment we did? We took this powder, which is a big size, right? So, we had to design experiments, common sense experiment. We ground this powder in the agate mortar pestle, make it up to this size. Now, it is a powder, right? I started with this powder, ground to this size, still a powder. So, the composition remains the same. I am not playing with the composition. Same material I ground to small powder, and I got its rhombohedral. So, this tetragonal completely became rhombohedral. The more I ground, the more I got the rhombohedral phase. So, it solved a puzzle that it is the grain size which was determining the phase, the structure of the material. Now, the question is, got this? So, this we settled. This helped us to answer this observation from the literature, because different people were reporting different range of two-phase coexistence. Somebody reporting 20 to 40 is huge, right? Huge range of code. So, the question is very simple. When you are sintering, whether you are allowing the grain size to grow enough. If you allowed the grain size to grow enough, then it becomes tetragonal. If your sintering time and temperature is such that it did not allow the grains to grow that extent, you always get two phase, right? And this was the answer, and that we could resolve, that different people perhaps have got different grain sizes because of different sintering conditions, and that is why they were all there is inconsistency in the literature. So, what seems to be inconsistency in the literature has a science behind it. There is a consistency. We could capture that consistency through simple XRD and SEM studies. There are many more things. I think I will just stop here. This was just to show you that your XRD and SEMs looks trivial, but it can solve many interesting puzzles as well, if you know how to use it. And there are many features. For example, you have the FWHM, which tells you information. You have the peaks, right, tail of the peaks, which tells you many information about this. So, it is very, very powerful tool for me. I am known as an XRD person. People don't know me what work I do. They say that, okay, the way you use XRD, you bring so much of science from it. So, I just anybody can use the XRD in the same way. I think it was rather serious, not an item thing.
Let's thanks. And it's really our pleasure to have him as a colleague, because he can do really the item song impromptu. So all that you see here was done in 5 minutes or 10 minutes. So it really is pleasure for us to have a colleague like him, or all colleagues. Saw examples of how XRD and SEM can be used together to solve some real interesting problems. And of course, the pleasure is to solve the problem. And one of the outcomes of solving this interesting problem is interesting publications. And I think you might have noticed the number of publications in PRB and other journals just coming from, of course, the important thing is to ask the right question.
Yeah, that's true.
That is the most important thing, because then you get you make the real impact. The questions actually determine the impact. So the tools that you are using are the tools that we are discussing in this workshop. So that will enable you to actually solve these problems. So with that, once again thanks to Professor Rajiv Ranjan. And he is around. If you want to know about his work, if you want to talk to him, you can always talk to him. I think we will also be there for lunch, so you can always talk to him. So now we. Sorry for having coffee without you. uh, so today is the last day for the some lectures in the classroom. How was your experience yesterday in the lab? Did you get a chance to like feel the machines or do anything? Kind of. Okay, so I think you may have also seen what other facilities we have. Actually, we have this advanced facility for microscopy and microanalysis, AFMM, have two buildings. It has two buildings. One of the buildings is dedicated for TEM, and this is another building where is dedicated to uh, things other than TEM. So this has SEM, this has Microcity, this has Atom Probe, this has FIB, and another anything else? EPMA. So EPMA we can use to get a sense of chemical analysis a little bit more with higher spatial resolution, as well also better, let's say, to a lower concentration also we should be able to get it. So you visited the other building, but as you are there, just sneak around, see what are the things, because all of these facilities are available to you to use. So this is just an excuse that we are doing XRD and SEM, but the facilities that you see at AFMM and tomorrow you will see at the central facility at XRD, all those facilities are available to you in the same way that they are available to us as here. Am I right? So when you get a chance to see what can be done here, then you will not be limited by the availability of the equipment when you are planning your experiments. So at least that part we can try to help you with.
I'll give some examples.
And so today, with that, today we have a little busy day. So we will have two talks. First by Professor Surendra Makinini. He is associate professor in our department. Actually, he just became associate professor 10 days ago. 10 days ago. We are still waiting for the party from him. So he's also, he does by his research interest. He is a metallurgist working in physical metallurgy, alloy development, mechanical metallurgy. But here he will wear the hat where he is the authority on microscopy. He is actually the real person behind the facilities that you see there, AFMM. He runs it, he coordinates it along with other colleagues. I think Professor Rajiv Ranjan is the convener there, but he is the man behind it. And his expertise in electron microscopy is also very, very is exceptional. So he will talk about FIB today, focused ion beam. Did they see yesterday?
Yesterday, one group has seen one batch.
FIB, and this is a very powerful tool. We use it for many things, and he will show some of that. Then at 11:30, Professor Chandan Srivastav, you heard him yesterday. He will give a little bit more talk about, I think, spectroscopy techniques today, and that's where the EPMA or EDS come in the picture. And also we will have one person from IIStem. Are you aware of IIStem? So I requested him to come and give a talk for 15 minutes to tell you how you can access equipments at IISc, around IISc with IIStem, with the IIStem portal, so that you also are exposed to that. This is okay. And then I think around the lunchtime, maybe before or just after, we will also hand you over the certificates, because I think some of you are leaving today. So that's the plan, and then again afternoon we will have the lab sessions. Okay, so with that, I request Professor Surendra Makini to talk about focused ion beam.
Thanks, Praveen. So, okay, so welcome all and good morning. So, as Professor Praveen introduced already, so we have a dedicated central facility which is advanced facility for microscopy and microanalysis, and the pair program also was centered on this particular facility. So, this talk will be on focused ion beam. Then once the basics I will cover the focused ion beam, then I will briefly give you some examples how that all the techniques which are available at IIFMM can be used in a correlative way. Okay, so I will give you briefly some metallurgical examples. So there is a website myscope.training. I think you should go to that website, and it's a very nice website where you can actually simulate the electron microscopes. So it has a focused ion beam, even SEM, TEM, so all things you can do the simulation, and you can actually feel that you are operating the microscope. So it's a very nice website, and some of the slides I have taken from them, but little bit I modified it. Okay. Okay, so yesterday one batch has seen our facility in one building. So our AFM has been supported by past ISC, DRDO, CSR and DST and DI, and for the last 25 years. And we have aberration corrected microscope where we can get the structural information at a very local scale in the atomic resolution. We have a dedicated high resolution microscopes for topography and the backscattered electron imaging. Sample preparation FIB, which I will cover now, and there is also a tool which is atom probe tomography where we can get the chemistry at the local level in a ppm resolution. Okay, so there are other facilities which we do the correlative microscopy, where using all the microscopes from a same region of interest to get both structure at a macro scale to the at atomic scale, and also the chemistry of those sample features. Okay, so these are the tools. So again, aberration corrected microscopes, there are two more microscopes which are conventional, which we use for the analytical microscopy, for the dark field, bright field, weak beam microscopy. We have two FIBs, there is a X-radia, there is a EPRIO, we have a EPMA, and also the atom probe. We have a couple of nano indenters which we can use for the indentation of the samples. So if you see the correlative experiments, in a SEM based techniques, we use EBSD, electron backscatter diffraction, for the orientation of the grain boundaries. Then we also used transmission Kikuchi diffraction and electron channeling contrast imaging in a SEM, correct? In a microscope, in a electron microscope, where TM and HR stem can be done for the diffraction analysis. But all these tools needs sample preparation. Okay, so in around 15 to 20 years before, we used to prepare samples by either electropolishing, but now in the last decade the preparation of samples by the FIB has increased significantly. So use of FIB is very important to use these tools. Unless FIB, and there are definite protocols which can be used in FIB, where we can get different types of samples for different analysis. For EBSD, we can do the sectioning, and we can do the EBSD, we can do the 3D microscopy at a macro scale. For TEM, we can prepare the samples. I will show some examples. For atom probe tomography, we can prepare the needle specimens. So the FIB is very important to prepare the samples for all these tools. Now coming to a little bit more details of what is focused ion beam. So as the name suggests, a focused ion beam is a stream of energetic ions that are focused into a very fine beam. These energetic ion beams are usually we use the gallium plus ions, which are heavier. So I will come to that later. So I will give you brief function of these use of FIB. We can do the micro machining. So here there is an image where you can see that the material around these pillars has been sputtered out. Correct? The material is removed from the sample. So FIB are able to structure the wide range of patterns from the nanometer to the micro scale. These are very applicable to the microfluidic channels, complex 2D and 3D structures we can create at the micron scale, at sub-micron scale also. And these are used for applying grids, patterns to the surfaces. and also to place the fiducial markers for the specific locations. Okay. Another important function is the cross sectioning. So if you have a material on the surface and if you want to see what is present in the subsurface, then you can use the cross sectioning and you can reveal the structure underneath the surface. Okay. So features that are hidden underneath the sample surface can be explored, analyzed, and using cross sectional analysis. Okay. So the advantage over conventional cross sectional analysis is that the area of interest, whatever the area of interest you have, can be selected with nanometer precision. So this is the second application. The most important application is the making samples for the electron microscopes, correct? So we can use site specific TM sample preparation. So if you have a metallurgical sample with the different grains or the different phases, you can do the electropolishing, but you will not find the site specific. The electron transparent will happen at any location, but you can miss the feature. But by fibbing, you can select the grain or the phase, and from that phase or from that grain, you can extract the sample. Correct? So you can make the site specific TM sample preparation. You can choose the specific area of a specimen, such as an interface, okay, particle, then prepare a TM section, and you can I will come to these tools, how to use the TM samples, correct. So I think in the last yesterday some batch must have seen how the lift out and manipulator. So I will briefly come to that. Another wide, now the last 10 years, the fib is used to prepare the APT samples. It's a very nice technique to prepare the needle shaped specimens. Actually, I will give you brief introduction to atom probe. I will not go into the details, so that you will get a feeling that what you can utilize these facilities in our central facility. So these typical needles have a length of 15 microns, and the tip less than 100 nanometer can be milled in the fib. Okay. So now coming to the instrumentation part. So I hope Professor Chandan has covered the instrumentation for SEM. He has covered the column, the lenses, everything. So I'll just briefly go to the fib. So you can see this instrument, it's a dual beam. Dual beam means you have an electron column and you also have focused ion column, correct? That's why it's called a dual fib. Previous fibs, they have a single beam. Single beam means only fib will be there, there will be no electron column. Okay. So this is a typical cross sectional geometry. This is your electron column, fine. This is your fib column, and there is a gas injection system and there is a manipulator. These gas injection system, manipulator, and the fib column are the main three parts of using the focused ion beam in the instrument, correct. So a fib is a focused beam of ions, and this beam is scanned across the sample just like it is an SEM. So your electron beam falls from this column to the sample, but your focused by FIB column will be at the 52 degrees from the sample surface. So at the 52 degrees, the FIB, the focused ion beam, will fall on the sample. Remember, electron beam minus focused ion beam, it's a plus. Okay. So ion is always heavy than the electron, and it moves very slowly. Okay. That's why in fib we use the electrostatic lenses, because electromagnetic lenses is dependent upon the velocity of the particle, correct. Now the ions have a high energy. When they hit the sample, they create a signal from this interaction. So whenever ion goes to the hit to the sample, you will generate different types of signals from the sample surface, exactly like electron interaction with the sample surface. Correct? When the energy is high enough, the fib can remove the atoms from the sample surface. So this process is called sputtering. Okay, you are sputtering out the atoms from the sample surface. So that is the technique what we are using it. So we can cut, we can trench, we can mill the sample on a scale of nanometers to the micrometers. As I told you, there are three. There is a vertical electron gun. This is a vertical electron gun. The ion gun. This is the ion gun, which is tilted at 52 degrees. There is a gas injection system. This is the gas injection system. This is used for welding and depositing the material on the surface. So any material, if you want to remove, you have to weld it. Then only you can remove it. You cannot remove just like that. And for welding, you need some manipulator or some rod. So this is called the manipulator for in situ lift outs. Correct? Several types, and basically in this chamber you have a several doors where you can put EBSD, you can put the EDS detectors, you can backscatter detectors, and all these detectors can be used simultaneously while fibbing the sample. So that's why we call it as a correlative use of these techniques. Fine. Now I suppose the electron column has been described very well with the Professor Chandan. Now I will come to the ion column, which is at the 52 degrees, correct. So the ion source that creates the beam, so there is a ion source, okay, electrostatic lenses that control and shape of the beam. So the electrostatic lenses are condenser lens and objective lens. A beam selective aperture that sets the ion beam size. So there is an aperture here. Apertures are nothing but holes in the, on a steel plate, and you can change the ion current by using these apertures, correct. So this is nothing but a beam selective aperture. Then there is a blanking plates. These are called blanking plates in the fifth column that are used to push the beam away. So you don't want to remove the material continuously. Somewhere you have to stop it. That time you use the blanking plates so that the beam will be stopped. Otherwise it will remove the continuous material, correct. So that's why these banking plates are very important part. Fine. Now we will go to step by step. So first we will describe the ion source. So how these ions are created, correct. So that's the question. So there are different kinds of ions which are available in the market, okay. So the most famous is the most used in the microscopes is the liquid metal ion source, LMIS, which are used as a gallium plus ion source, okay. So there is a reason for gallium plus ions which I will come later in the next slide. These are the being most common in the microscopy applications. These instruments generally operate with energy ranges from 500 electron volt to 30 kV, which is a general voltage which is applied in a normal SEM. Beam currents from 1 picoamps to the 65 nanoamps, and image resolution of 5 nanometers are achievable. So if you have any particle of 10 nanometers or 15 nanometers, actually you can use this ion source to remove that particular particle on ion, correct. There are other field ion source, gas field ion sources, GFIs, such as helium and neon. These are the advanced FIPS where they use it. Inductively coupled plasma ion sources like noble gases such as xenon. There are low temperature ion sources, magneto-optical trap ion sources, and liquid metal alloy ion sources. So these are the general other sources which now in the market is started available. There are advantages for this because the faster milling times and faster rate are achieved from these sources, correct. But most conventional for our metallurgical use, for the lab use, we can rely on this liquid metal ion source which is moderate and which can work for us, correct. Now we will come to the actual source, Now if you I am talking about the ion gun, correct. So in the ion gun also there are several parts in the gun, as in SEM, in electron beam. What are those parts? There is an insulating mount, there is a tungsten needle, there is a gallium reservoir, there is a suppressor. These are the suppressors. There is a gallium reservoir. This is I'll talk about the Taylor cone later, and there is an extractor, correct. So there is a gallium source, there is a tungsten tip. Now the LMIS is a point source consisting of a tungsten needle. So there is a tungsten needle with a liquid metal reservoir which is a gallium, conventionally gallium, and a suppressor and an extractor. These are the 1, 2, 3 and 4. These are the 4 important parts of this source. A tiny cusp, okay, high electric field. So now when you apply a negative voltage here in the extractor, so what will happen? There will be a electric field between the tungsten tip and the extractor. What will happen? The electrons will tunnel towards the tungsten tip. The gallium ions, the gallium atoms will ionize. They will become ionized. The electrons will tunnel towards the tip. These gallium plus ions will get, and it will form a Taylor cone at the tip. And due to the very sharp tip, the amount of electric field is very high, and due to those electric field lines, these gallium plus ions gets field evaporate from the tip towards the extractor. So the extractor is to extract the gallium ions from the reservoir, and tungsten tip is used to create the Taylor cone. Fine. So now the gallium ions are extracted from the cusp of the Taylor cone by the field ionization. Field ionization is not, there are 2 processes here. One is field ionization, one is field evaporation. Field ionization is the electrons are tunneling from the gallium towards the tungsten tip, so that you will create a gallium plus ions. This is called field ionization. When these gallium plus ions gets field evaporated, these are called gallium field evaporation. So there are two processes which is involved. Gallium reservoir. Why we are using the gallium? Gallium is most commonly used for the liquid metal since it allows room temperature operation, okay, due to the very low melting point of 29. So at the usually at the liquid at the room temperature it usually forms as the liquid, correct, 29.8. This minimizes the interdiffusion of gallium with the tungsten. So the reaction between the tungsten and gallium is minimum. That's why we are using gallium, and gallium is sufficiently heavy. So the atomic weight of gallium is very heavy compared. So that what will happen, it will have a very efficient sputtering when they are using on the sample surface. So little bit more about the field evaporation. So as I told you, when there is a formation of this Taylor cone, how the formation of Taylor cone? Because of the tungsten tip, there are two processes involved: field ionization and field evaporation. Electric field pulls the gallium from the needle tip, from the reservoir, while opposite surface tension of the molten gallium acts against the electrostatic force. So the gallium has also having a some surface tension on the tungsten tip, which will have a opposite force from the top, correct. But due to the application of voltage, negative voltage, there will be a force in this direction, in downward direction. So what will happen, there will be a balance is achieved between the two forces, and at one stage the liquid gallium will get field ionized to form the gallium plus ions, and these gallium plus ions will then accelerate towards the extractor, which is called the field evaporation, correct. So that's why the Taylor cone, which is of the 2 to 5 nanometers, is very important here, and it is related to the cusp formation. So the ionized gallium atoms at the cusp are then field evaporated, fine. So up to here it is clear how the gallium ions or the gun is working on this. Now once you generate these gallium plus ions, these ions can travel anywhere. So that's why you have a column, and there is a lens system, so that you can accelerate those gallium ions towards one direction, correct. So that's why we use the lenses here, okay. So the gallium plus ions will accelerate through a potential and travels down the column. The ion beam will then go through a series of lenses. The first is the condenser lens, then there is an objective lens, correct, and apertures along the beam path before reaching the specimen. So specimen will be here, below the objective lens. The condenser lens forms the beam. So the condenser lens is the very important. In SEM also the condenser lens forms the beam, correct. Similarly, it forms the beam which is then scanned across the sample surface by the octopole. So this is called the scanner, octopole. This is just a system of lenses where these are beam deflectors, okay. So in SEM there are beam deflectors for the scanning. Similarly, this octopole acts as a beam deflectors. You can scan on the sample. The objective lens focuses the ion beam onto the sample. So this is objective lens. The role is here, sample is there, it will focus on the sample surface, fine. And astigmatism is corrected by coils in the octopole region. So here below these octopoles there is a stigmatory coils. In SEM also we will have a stigmatory coils to correct the astigmatism, correct. So I suppose the aberrations have been corrected, have been taught during the lectures, correct. So this quadrupole, and then there is a quadrupole. This is a quadrupole which controls the mid column steering of the beam during alignment, okay. As I told you, these electrostatic lenses are used. Here we don't use electromagnetic lenses because the ions are heavy, correct, and the speed is very low, but magnetic lenses are function of speed. So that's why they, in the electron column we use the electromagnetic lenses, but here electrostatic lenses are used to control the beam, okay. The blanking plates deflects the beam away from the center of the column to avoid unnecessary exposure of the sample. Otherwise you will remove the sample continuously. So that's why the blanking plates are important, fine. Now we'll just talk about the beam selection apertures, fine. So this is a very simple. So if you select a large size aperture, you will get larger beam. If you select a small size aperture, you will get a small beam. But the thing is, if it is a smaller beam, your current also will be small, correct. You will lose less current. If it's a larger beam, you will get a more current. It means more amount of material can be removed per unit time, okay. So if you have a very heavy metal like tungsten or tantalum, which are very heavy, then the removal of those atoms will be difficult because their bonding and it's very high. So you have to use the large beam, correct. So the ion beam current is selected by the beam defining aperture. This is an aperture strip with differently sized circular holes called apertures, and the larger the aperture, the larger the ion beam current. Now these apertures has to be replaced several times, like every 3 months, because this is also a metal plate, correct. This is not a like a ceramic. This is also metal plate where these large beams are interacting with the aperture. So by time what will happen, these apertures will become larger. So you will not get a proper current if you are using a small beam from the software, but usually the aperture size physically will be much larger. So you don't have any control on the your milling. So that's why these apertures has to be replaced every 3 months or 4 months. Little bit equations, it's a very simple equation we call is a ion beam current. The ion beam current is nothing but the number of ions that can interact with the sample during the time, okay. It is nothing but I current in the amperes, T is the time in seconds, and C is the charge, okay. This is the ion beam current. Ion dose, so you can define this ion dose based on fluence and dose. Fluence is nothing but if there is a beam passing to a area which is called fluence. But if the beam interacts to the specimen surface, so based on the specimen surface, the beam interaction, the interaction volume will increase or decrease. That's called the dose which is forming on the sample surface, correct. So the fluence is the number of ions that pass through an area prior to the interaction. The dose is the number of ions that have traveled into the sample surface, okay. So there is a difference between the dose, between the fluence and the dose. Dose is nothing but the number of ions per area in square centimeters. This is a simple equation. The dose rate, if you put up the time, then you will get N by A by T. T is the time in seconds, okay. So now it is just general equations. Now coming to the interaction of the beam with the sample surface, okay. So now when an ion beam interacts with the sample surface, you will generate several types of energy radiations from the sample surface. First, yes. So if you want to change a current, if you want to mill a very fine milling, then you have to lower the current. So you can physically change the aperture. 8.5 lakhs. Ah, yes. Okay, yes. Yeah, we have to change it. It's a very costly business. Okay, so once a beam interacts with the sample, then first is secondary electrons. This is similar to electrons interacting with the sample surface. You will secondary electrons, you know, correct, the electrons from the surface atoms, these are called secondary electrons. But due to the energy, high energy of these ions, secondary ions also can be generated. This is something new in this. Secondary ions from the sample surface, which can be detected using different detectors and are used for recording images, correct. Sample surface atoms can be removed in a process called sputtering. As I told you, if the atoms are removed from the sample surface, these are called sputtering, and this process is used to cut structures, features and cross section. The sample, so you know that this is a very high energy beam, it goes to the sample surface, it can generate artifacts, it can generate defects. So vacancies can be generated, dislocations can be generated, interstitials can be generated, gallium can diffuse into the samples and it will retain in the sample surface, so contamination will happen, correct. So the interaction takes place until the ion has lost all its energy. So ion has a certain energy. So once it goes to the sample, it loses the energy in the form of these radiations, correct. So it will travel in such a way that up to the level where all the ion energy will go to the zero, correct. Okay, so and we also called this a projected range. So if ion travels to the sample surface and the last distance, the last section where it can travel, that distance is called the projected range of that particular ion, fine. So due to these metal ions are very heavy, it cannot penetrate as electron penetrates. Electron is very small, so it can penetrate to a large dimensions up to around 20-30 microns, but fib, the ion beam, cannot penetrate up to that level. It can penetrate maximum up to around few microns, 5 to 6 microns. So based on the signals, what I call there is a secondary electron emission from the surface atoms. These signals are conventionally used for the imaging. So, you can create the ion beam image, correct. Now, these secondary electrons, as this energy beam is very high energy, so what will happen, the secondary electron yield is much higher than the electron. So, in your scanning electron microscope, if 0.1 to 1 secondary electrons are emitted per electron beam, but in this case 1 to 10 secondary electrons are emitted per ion beam, correct, because of the high energy. Then there is a generation of secondary ions from the sample. These are high energy collisions, can turn into sample atom into the ion, and these ions gives the chemistry information, okay. Then you can use the detectors to detect these secondary ions to get the chemical information, correct. So, these secondary ions also can come up to the knocked out from the specimen surface. Secondary ions therefore carry chemical information about the specimen surface. Backscattered ions, similar to the electron beam, correct. So, so backscattered ions means those are backscattered electrons. So, these backscattered ions, the ions which travel to the sample and get scattered out of the sample surface. So, these are the primary beam, means the gallium which are used, gallium plus, it travels into the sample, again it comes out and it gets deposited on the surface. So, this is called surface deposition of the gallium ions, correct. So, these are backscattered ions. And there is a phonons, this is nothing but some atomic vibrations and waves in the same sample crystal, where it is related to your represent the form of heat, some form of local heat it happen, phonons. Huh. Yes. From the surface atoms. So, these are no. So, for example, now you have a gallium ions, it is getting interacted on the surface of your sample. Assume there is a aluminum, it will interact to the aluminum atoms. Then you will have an energy which can remove the electron from the aluminum atoms. Those electrons are called secondary. Where those electrons will go? Those electrons will be get emitted, na? So, those electrons can be used for the secondary imaging, topography information. Now, you have aluminum plus also. Those aluminum plus ions can be used for the chemistry information. It's clear, na? It is similar to what in the electron beam interaction. Okay, ion implantation. So, these I told you these are very high energy. So, what will happen? These gallium ions moves very slowly, and these are very heavy. So, the penetration depth is around it's less than 1 microns. Okay. Now, if you use the xenon or the plasma source, it can go up to the few microns, 5 microns. But for the electron penetration depth is, you can see that it's up to in a few microns levels. Okay. And the beam which falls up to this is the sample, and the position where it loses all the energy, that is called the projection range of that particular beam, and it depends upon the sample which you are using it and what the source you are using it. Okay, for the sputtering, what are the main conditions for the sputtering? So, the material has to remove. So, sputtering occurs when a sample atom is ejected from the sample surface, correct. So, this is a special case of, so you are displacing the surface atoms from your sample to outside, correct. So, you need the display. So, only atoms near the sample surface are potential candidates for sputtering. You are actually removing the sample surface atoms. The more collisions that occur on the sample surface, the more likely the sputtering occurs. Okay. So, that is why it depends upon the atom's location. So, the atoms that are located deeper within the sample are less likely to sputter, because the ion beam loses energy as it penetrates the specimen, correct. So, the ion beam, as it penetrates, it loses the energy. So, the sputtering tendency of these atoms will be much less than the sputtering tendency of the surface atoms. So, that is the thing. What are the conditions? The surface atoms needs to receive enough energy. The surface atoms needs to be displaced into a position outside the sample. So, the parameters affecting the sputtering. So, how you can increase your sputtering tendency? It depends upon the surface binding energy, the incident angle, the angle of incidence on the sample surface, and also the initial ion energy or the accelerating voltage. You can 15 electron volt or kilo electron volt or the 30 kilo electron volt, the sputtering tendency also will change. So, we will just talk about the incident angle. So as you know, in the electron microscope also, if you tilt your sample for, so usually you are tilting EBSD, you have heard about that, correct? Electron backscatter diffraction. So for electron backscatter diffraction, actually you have to tilt the sample to get large yield of the electrons from the sample surface. So that's why you have to tilt it. So you can see that as increasing the tilt, you can see that the yield, the sputtering yield increases. Sputtering yield is defined by number of sputtered atoms by number of incident ions, correct? So it depends upon the incident angle. Incident angle is 0 when the beam falls exactly perpendicular to the sample surface, correct? And also the sputtering yield depends upon the accelerating voltage, as we told. So till now we have discussed about the column and generation of the gallium ions and how the gallium ion is interacting with the sample surface. Now there are two important other components in the FIP. As I told you, there is a gas injection system. What is gas injection system? Okay, so there is a GIS needle. This is your ion beam. This is your GIS needle. Now assume that in this GIS needle I will put up some gas, some precursor, correct? Some precursor. And if this gas is continuously ejecting on the sample surface, as it ejects on the sample surface, your ion beam falls on that particular ejecting gas. If it falls on the ejecting gas, because of the energy, what will happen? It will crack. It will crack. Crack means it's a chemically. It's chemically it will break down. Once it break down, what will happen in the gas? Whatever the metal is there, that will get deposited on the sample surface. So it is nothing but if you are putting something and you are with high energy, you are bombarding it. Whatever the material is available, it is going and sticking to the sample surface. That is the role of gas injection system. So gas injection system introduces reactive neutral gases. These neutral gases may contain tungsten, may contain carbon, may contain platinum. That's why we heard about platinum deposition, tungsten deposition, carbon deposition. So they have these metals which are in the chemical form, some chemical form which can be easily formed in the form of gas, correct? So this is called gas injection system, and these are usually inserted within 200 microns of the sample surface. This is your sample surface, this is your gas injection system, and you can see that it is very near to the sample surface. So your gas is continuously ejecting here, your beam is falling on the gas, and whatever the gas, it will break down to the metal, and that metal will be deposited on the sample surface. This is the role of gas injection system, and this also used for the welding. So you can weld the samples by using the manipulator. I will come to that later. So GIS allows the deposition of a broad range of materials, either platinum, tungsten or carbon. This is used for nano fabrication and sample protection purpose also, correct? So during deposition, a gaseous precursor, with here it is a platinum, it might tungsten precursor also. Then when ion beam interacts with this, it releases onto the sample and is then cracked by the ion beam, electron beam, and gets deposited. Okay. So now there is one more important part is the manipulator. So this is called manipulator. This manipulator is nothing but one rod. It's a tungsten rod, very thin rod, around 2 microns. That manipulator, it is used to lift out the sample. Now if you have a sample surface, you milled out, and if I want to remove this material from the surface, from the sample, now then I need a manipulator. I will go down to the manipulator, then I will use the gas injection system to deposit that platinum at this location. It is like a welding, you are welding the sample. So you must have seen the welding. Yeah, so here also we are doing the micro welding or the nano welding, we tell. So you weld the sample, then you use the manipulator again, so you are removing the sample from the sample surface. That is the role of the manipulator. Okay, that is a very simple. Okay, so the manipulator is a sharp needle that allows sample section to be lifted out and relocated either in the TM grid. So you can use the TM grid to put the TM lamellar or the APT samples or any choice of the samples, correct? So this is your gas injection system, this is your manipulator, this is your grid, and you are actually welding the sample onto the grid by using these two. Fine. I suppose yesterday's batch you must have seen this setup in a SKIOS. Overall beam geometry overview, this is the column, electron beam falls on the sample, there is an ion beam falls on the sample. Simultaneously both you can image, you can get the ion image also, you can get the electron beam image also. Remember, it is at the 52 degrees. If you want exactly perpendicular image, you have to tilt the sample perpendicular to the beam 52 degrees, then only you can get the perpend. But you can in this orientation, if you see the ion beam image, it will be certain like tilted image, but in the electron beam image it is exactly the flat image. This is a very small video, it is a section where we how we are preparing the sample. So this is a area of location, grain boundary. You are sputtering out the sample from this, you are rotated the sample, again sputtering out here. So my area of interest is this grain boundary. So this is a site specific preparation. Then we are removing, so we are preparing this lamellar. We are removing the sample from here to detach from the sample surface. You are bringing the manipulator here, then you are welding with the GIS needle, then again you are cutting from here, then again you are removing the lamella from the sample surface. Then this is the APT sample preparation, this we will cover it later, but you can put on the grid or the silicon manipulator, then you can mill on the manipulator and you can create a needle specimen. Exactly similarly, there is a standard protocol for the TEM sample preparation. Okay, so APT sample preparation is little bit easy, but the TEM sample preparation, there are several steps involved. Okay, I suppose you got an idea of the fib now with this description, correct? So fib also can be used for several purposes. You can use patterns, you can put spot scans, you can deposit rectangle, any shape. So it is all depends upon your electron beam. So any shape you can deposit, you can cross section, you can do the micro pillar. So by fibbing you can do the micro pillar, preparation of micro pillar, and also you can put the nano indentation on the micro pillar. So these Professor Praveen's expertise is on those things, that making the micro manipulators or micro lamellar and doing the small scale testing, correct? So these can be done in the milling. I talked about the 3D sectioning. What you can do is, if you have a sample surface, you can mill slice by slice, you can do EBSD on that particular slice, then you can get the 3D reconstruction of the EBSD pattern, correct? So this is the use of fib with the microscope. Okay. How much time is there? Okay, half an hour is there, it's fine. Okay, so now coming to some applications. So I think this will be the most interesting, because you will correlate how we are using these all techniques, which how the focused ion beam is the playing a central role in between these techniques. Okay, so most of my group or most of the people here, they use the correlative microscopy. So what is the correlative microscopy? You are making a sample which can be imaged or which can be analyzed, destructive or non-destructive, with different instruments. So you can carry the sample from an electron microscope or from optical microscope to the electron microscope, then you can go for the TEM, then you can go for the atom probe. So you will get a complete structural information from the macro to the atomic scale. Okay, so this is how we do the correlative microscopy. So there are certain protocols which we use correlative microscopy. This is just an example of use of TEM and atom probe, and this can be used for your samples. So for any of the kind of analysis which we can do, we can use these techniques for your samples. So what we do is, it's a very simple thing. We take the Molly grid. So grids, you know, correct? TEM grids. TEM grids you must have seen. So usually these TEM grids are used for the what we call is nanoparticles to deposit for the to analysis of the TEM. We cut this Molly grid. You can see we cut the Molly grid. Then we place it in a holder. This is an electropolisher, correct? And if you place this is a crocodile clip, and which is a platinum wire, correct? And this crocodile clip holds this particular grid. You can see this is the grid here, and there is a platinum wire and with the electrolyte, and because of the surface tension, that electrolyte retains in that small hole. Now with this is motorized, So now what we are doing is we are continuously moving this particular clip up and down, so that it will go to the electrolyte, it will come out of the electrolyte. So what will happen, it will do the electropolishing. So this is method of electropolishing. Now this particular region is converted to a sharp tips, you can see here, and these sharp tips are used for the holding the samples by using the fib manipulator, correct. So you can see that you can use the fib lift out, you can lift out the lamellar, you can place on this a molly post, then you can use the fib by milling the sample, then you can go for the Titan for get the electron microscope, get the structural information, then that same needle you can go for the tomography where the chemistry you will get it, correct. So I will give you one example. Now I suppose you must have heard about super alloys. We use these alloys for turbine disc applications in aerospace, in turbine engines, correct. So these are blade alloys. So these super alloys usually they are exposed to very high temperature and stress conditions, and during exposure what will happen, they will deform. So it's like creep deformation. So creep, I suppose you know creep. So creep deformation, what happens, you will get certain type of defects in the microstructure. Okay, so these are called planar defects. Now this is a microstructure where you can see that this is a microstructural feature which is called a gamma prime phase. The dark feature is called gamma phase. You can see these lines, these black lines, horizontal lines. These are not scratches, these are all defects which are produced during the creep deformation. Now if you see the scale, this particular line is a few very 1 or 2 nanometers thickness, it is a few atomic layers, correct, and the length also is within 50 nanometers. Now by using the fib we can locate this region, we can deposit the platinum on the top of that particular region at that scale. So this is a platinum deposition, as I told you, by using the GIS needle. Then you can deposit like this in several regions. You can make the lamella lift out from that particular region by using the manipulator. That particular lamellar you can paste on the molly grid. Okay, so this is your cut lamellar, this particular lamellar is cut lamellar. We know that the defect is here, somewhere here. Then after cutting the sample we will mount it and we will start polishing by the fib. So you can create, so I know that my defect region is somewhere here, and if I polish it by the ion beam, then I can create a needle where I will get the defect in this region, correct. Now I know that my defect is in this region, this particular sample I will go to the Titan or the analytical microscope where I will get the structural information. Then I will go to the atom probe where we will get the compositional information, correct. So to use these facilities we have simple several correlative holders which we developed in house. So these are the stainless steel correlative holders which can guide us to bring the sample from the fib to the atom probe and to the electron microscopy, correct. These holders are available with us. So you can see there is a needle specimen, there is a dark lines, these are the bright lines, and this is the electron microscope. So this particular needle, if you go for high resolution, you can see that there is a change in the atomic column. So there is a planar defect. Okay, so this is called intrinsic stacking fault in the present, and the same defect actually you can do the atom map and get the composition across those defects. So this is a typical examples of correlative microscopy. Now I will briefly cover the electron microscopy, what information we are getting from the microscope, and how fib and atom probe will give you the required details, correct. So now it will go to the application side. We know that if any sample, metallurgical sample, you can get the grain orientation maps in SEM by the technique called electron backscatter diffraction techniques, correct. So this is conventionally and it has been used everywhere. So you will get the crystal structure analysis, grain orientation map. Conventional TM, you can get the diffraction, electron diffraction imaging orientation maps. You can analyze the phases present in the sample, and in high resolution you can actually do the atomic structural analysis and also the interface and defects. Okay, so these are in the electron microscopes. What is the drawbacks? Usually these are all 2D projection of the data. You don't have 3-dimensional information, correct. So now if you in the next class, Professor Chandan will talk about the spectroscopy. He will cover the EDS and EELS, I suppose. So, I will just briefly tell that EDS spectroscopy is the energy dispersive spectroscopy. It is related to the X-rays generated from the sample. So, when an outer electron, when the beam interacts with the sample, what will happen? The inner shell electrons get excited, then the outer shell electron will go inside and they will generate the X-rays. Depending upon the energies, they will have a different wavelengths, and these wavelengths can be detected as X-rays by the spectroscopy. Right? So, this is called EDS spectroscopy. The problem with the EDS spectroscopy is the accuracy depends on the Z. So, your low Z elements, you will have a energy, the difference in energies are very close. So, the resolution of EDS is around 130 electron volt. Now, if light elements have a K shell or L shell which are less than 130 electron volt of difference, then what will happen? Your peak will be get overlapped, then you will not get the composition, correct. So, now the EDS spectroscopy cannot be used for the light elements, especially lithium, boron, carbon. You cannot use this EDS spectroscopy. So, and it is insensitive for the light elements. For high Z elements it is fine, it is more than 130 electron volts. EELS is a very good tool. So, it is a EELS energy electron energy loss spectroscopy. It is used in TM where you can use it for the light elements, and this is for heavy elements. Usually there will be an overlap of elemental specific edges and the deconvolution is required. These are very complex spectrums which uses more data analysis. Okay. So, that is why so this is the EELS map. However, and this is your EDAX map. You can see that EDAX can be done at a atomic level, but now these are all are 2D projection of the volume. Now, the importance of atom probe. Atom probe is nothing but this is atomic scale 3-dimensional compositional analysis, where you can get the mass resolution up to 10 parts per million irrespective of the element, and you can get the accurate quantification. Here you can see there is a video where you can see that the golden color circles are aluminum atoms, and the green color and the red color are two different types of precipitates. So, in aluminum alloys there are theta prime, theta double prime precipitates, correct. So, those precipitates can be visualized in 3 dimensions, and you can know that this is the reconstruction. So, in any region I can get the accurate composition, correct. So, this is, you can see the shape, this is the needle specimen. I talked about the preparation of the needle shaped specimens, correct. So, now I will connect this one to that preparation. Here you will get the mass to charge ratio. This is nothing but a mass spectrum. This is a needle, okay, and you can see that the radius of curvature is less than 100 nanometer. So, what will happen if you apply a voltage V, then the field which is produced around the needle will be around 10 raised to the power 10 volt per meter square. It is a very, very high electric field, due to which the electrons will tunnel towards this direction, and the ions which are present at the top will get field evaporated, fine. So, this is just a comparison of a needle specimen with a hair, our hair, correct. So, it is a okay, fine. So, briefly this in one slide I will explain you the atom probe what we have here. So, this is your needle specimen and different colors corresponds to different types of atoms, correct. This is a local electrode. It is like extractor in fib, there is a negative voltage extractor. So, this is, you can call it as an extractor, we call as electrode. These are MCP plate and this is position sensitive detector, fine. So, now you are applying a DC voltage between the tip and between the electrode, correct. So, here you are applying a negative potential, you are applying a positive potential. Now, what will happen when you apply a DC voltage? The electrons from these atoms will tunnel towards the specimen surface, and the ions which are present or the atoms which are present are get field ionization. Then due to the very high voltage, what will happen? There will be electric field lines which is going along this direction, correct, electric field lines. So, along these electric field lines these ions will start moving. So, this is electrode is nothing but a hollow copper foil, there is a copper foil and which is hollow. Now, these ions will hit to the MCP are used to just direct these ions towards the position sensitive detector. Now, these MCPs are used to increase the counts also and multi-channel plates. Now these position sensitive detector, what is the function? Now if you apply a voltage, there will be a tunneling of electron, one atom will go and hit to the position sensitive detector, you will have a x1, y1 and time of flight. What is time of flight here? So now different color corresponds to different elements. So they have a different atomic weight. Now if one ion is heavy, one ion is light. So what will happen? Heavy ion will take more time to reach the position sensitive detector. Lighter atom will travel much faster, so your time of flight will be very less. So that's why that is called a time of flight. So you can measure the time of flight, you have a position of x1, y1. This is the simple equation, Newton's equation, where if you assume that the initial velocity is 0, by using the kinetic energy, you can get the mass to charge ratio is nothing but 2 electron volt time of flight by L square. Time of flight is measured by the machine. L is constant, distance between these two, that is around 100 centimeter, and voltage is applied, E is the charge. So with this formula you are getting the mass to charge ratio which atom is present, correct. Now this x1, y1 is measured by the position sensitive detector. Now you can see this is a sequence of position. So you can see that first these atoms will be removed, second set of atoms will be removed, so your z will increase, correct, z coordinate. So the z coordinate resolution is around 0.05. So this is your basic principle related to the atom, and then you will get a tomogram where you can reconstruct this particular needle by using the software reconstruction. Okay. Okay, 10:40. Okay. Now I will give you the brief examples where I will show the application of this. So here you can see there is a copper, this is a copper alloy. It is a very nice EBSD pattern, colorful, where you get the grain orientations. The red color means 001 oriented, your green color it means 101 oriented. Now with this EBSD map I can locate the red color region, it is a EBSD map. I can create a needle specimen from that particular region. I will do the atom probe, and you can see that in this particular alloy you have these precipitates. This is the copper and these are all cobalt aluminum precipitates, red color, correct. Now this is a detector ion map where you can see that it is a proof that these are oriented in the 100 direction. Now if I go to this particular region, then actually you can see the atomic planes. Okay, so you can see that these golden color lines what you are seeing, these are actually the atomic planes, 100 atomic planes with a distance of around 0.36 nanometers, correct. And you can see that these red color atoms are also coherent along those lines, those atomic planes. It means that you can get a composition of each atomic plane by using this technique. So I know that this cobalt, you can see that the cobalt is not present here, but the cobalt and aluminum is present at these locations. So this is your precipitate location, fine. So you can get the composition of the at the atomic scale. So this I will skip it, this is not relevant. Okay, so I will give you example of a very nice example of grain boundaries, which is very important for the corrosion. Okay, so austenitic stainless steels, I think you must have heard about this famous steel, which is a A316, which is used for the gas pipelines, steel in the chemical industries, and these are corrosion resistance. Okay, so and these are these contains chromium, nickel, moly, silicon, phosphorus and sulfur. So the main thing is the intergranular corrosion of these alloys are very less, but the problem is it was found that at certain grain boundaries the corrosion is very high, at certain grain boundaries the corrosion is very less, but we do not know what is governing for that. Okay, so the so usually they expected that the sigma 3 boundary, sigma 3 is nothing but the 111 planes, normal annealing twins, those boundaries are the very less prone to the intergranular corrosion because of the lower energy, but there is no proof on that. So what we did is, we have selected two types of boundaries, sigma 5 and sigma 7. This is one metallurgical microstructure. These have been heat treated at 700 degrees Celsius, correct, same boundary, sigma phi and sigma psi, and this same boundary, and this has been analyzed, this has been corroded in hydrofluoric acid. Now you can see that sigma phi boundary did not corroded, while sigma 7 boundary got corroded. So there is a difference in the corrosion between the two types of boundaries. So we need to find why it is happening like that, correct. Then otherwise, if we know that sigma phi is not corroding, then I can do the texture mapping, and I can get that, I can do the processing in such a way that these sigma phi boundaries will be everywhere, maximum fraction, so that corrosion will come down, correct. But now I need to find what is the reason for that. So first what we did is, we selected the sigma phi boundary, we can make the needle specimen, and we can do the EBSD on that particular needle specimen. That is called the transmission Kikuchi diffraction. It's a general work, examples for using. So yeah, it's our work. Yeah. So so this you can see the needle specimen, and you can see that there is a boundary, and this is proved that these are called sigma phi boundaries. And if you do the atom probe tomography in these samples, you can see that there is a segregation of moly, planar segregation of moly at the boundary. If you take the profile across this, you can see there is a moly increment, silicon also is increased, chromium also increased, but nickel and iron is depleted. So we got the composition across the boundary region. Now what is the difference in sigma 7? We expect that there also it should be planar segregation, but actually what we found is the segregation is not planar. It is on the like a linear segregation. You can see there is a moly enrichment along certain direction. It's like defects, line defects. So there is a difference in segregation behavior between the sigma 7 and sigma 5. So there are certain region which is related to moly rich, there are certain region which are related to the moly depleted. So these regions are moly depleted, these regions are moly rich. Now what is the consequence of this? Due to these consequences, there is a difference in the chemical potential between the local regions. That is why the corrosion will be much higher for these regions, correct. So now sigma 7 boundary, after sensitization, you can see that the segregation still retains, and these at these sigma 7 boundaries we also see the facets, and these facets are exactly correlated to these segregation phenomena. You can see that at certain facet there is a bright contrast, at certain facet there is a dark contrast, and this contrast is related to the different types of phases which have been formed. Okay. So in TM we found that these bright phases are the lavage phases, and the dark phases are related to the carbide phases, and due to the difference in the composition and the phase structure, these sigma 7 boundaries are prone to debonding and prone to corrosion resistance. Okay. So this is how we concluded that how TM, APT and EBSD has been used to identify the corrosion mechanism. Okay, so I will give you this last example which is related to a turbine engine, correct. So just briefly I will show you. So this is a typical cross section of a turbine engine, correct. This is your fan, which is mostly made up of aluminum alloy. Here these are the and there is a shaft here, okay. Along that shaft these are the blades here, these are the compression stage. Your air is sucks into the turbine, it get compressed, and here the temperature reaches around 400 to 600 degrees Celsius, correct. It get compressed the air, there will be a fuel injection here, fuel and the air, compressed air will get burnt in this region, and the temperatures goes up to 1500 degrees Celsius, correct. So the material which are used here are titanium alloys, and the material which are used in this section are the nickel based alloys, which are called super alloys, fine. So this is typically a turbine blade. You can see this is your turbine blade which is situated here, and you can see that at this region. So this is a DMRL funded project, and if you see the microstructure of these the turbine blades, you see the very nice cuboidal precipitates. These are gamma prime, and there is a soft gamma channels, these are FCC, fine. So there is a gamma channel, gamma prime, they have a coherent interface, and in 3 dimensions by atom probe you can actually visualize these precipitates. Now if these alloy is operated at these conditions, definitely there will be a stress and high temperature, and they will mechanically deform and they will produce defects. Okay. Fine. So this is a gamma prime atom probe. You can see that. So the difference between these two phases, the thin channel and the gamma prime, is nothing but the chemical composition is different between the gamma and gamma prime. Now, if this particular alloy has been crept at 800 MPa stress, creep deformation at high temperature, correct? Now, if you see the profile, you can see that these lines which are passing through, these are not scratches, these are all defects which are produced along these interfaces. Now, I know that my area of interest is this region. So, what can I do is I can prepare a needle specimen from that region. These are the defects, and you can do the structural analysis by Hadaff. Then the same needle, actually you can do the chemical analysis and show that the chromium is segregated at these interfaces. Okay. So, we know that the chromium is diffusing at 800 degrees Celsius towards that line defect. So, the diffusivity of chromium is very important during those creep diffusion, because if chromium diffusion is less, the creep deformation also will be less, correct. Similarly, we see the twin boundaries. These are called twin boundaries which are located. So, Akshat, my PhD student, he has prepared a needle specimen from there. You can see this is a dark field image where you can see the T1 and T2. Then the same needle specimen, he has done the atom probe where you can get the chemical information across these boundaries. And if you take the composition profiles, you can see that there is a change in composition along these twin boundaries. Fine. Now, with this, he has proposed a new mechanism where this is irrelevant. So, we proposed a new mechanism of deformation which is rate limited by the tungsten and tantalum diffusion. Okay. Just go to the last part where. Okay. So, till now I have described about the till now I have described about the metallic samples. Now, Professor Sajeev from Earth Science department, he was having a sample which is a rock. It's a rock. It's a chromite sample. It's a chromium oxide, which is a million-year-old from Tamil Nadu, and he is seeing a distinct contrast in the rock. You can see there is a dark region, there is a bright region, but the origin of these contrast is not known. So, what he has given me the sample, and what we do is inside this region R1, the bright region, if we do we have done the diffraction analysis and the APT, and you can see that inside these regions these precipitates are present in the sample. Okay. Even in the rocks we see that coherent precipitates of iron oxide in the structure, and these are rich in iron and the oxygen. Then we have prepared the TM sample preparation. You can see there are certain bright regions are there, and if you see that by the correlative way you can get the diffraction patterns from these particles. You can make a needle specimen from that particular location. Okay. Then you can do the tomogram and you can get the chemistry information from those precipitates which are called spinels. Okay. So, this is the last example which I want to give you, and with this I will end my talk, and I will just briefly tell you that the techniques which I described here, the main focus was on focused ion beam. Without focused ion beam we cannot prepare the samples for these electron microscopes, correct. That is why we can do the superalloys, phase compositions, site occupancy, interfacial segregations which are important for several chemical reactions and metallurgical process, grain boundaries, defects, steels, bond coats, magnetic alloys, anti-phase boundaries, stacking faults, aluminum based alloys. So, these all spectrum of alloys can be characterized by the techniques which we are having at the center, and these techniques are all available to you for use of your research, and I just gave a flavor. According to your research, you can have you can judge yourself that which instrument will be helpful for analysis of your samples. If any doubts are there, you can come, you can email me, or you can contact me at any time. Okay, thanks. If any questions are there, I can answer. yesterday you have seen one building during your practical session. There is another building where we have a TM facility. So if today's batch, if somebody wants, if their session is over, then you can request any of their staff member. If you are interested, make a group and you can look into the another building also. It is not a problem. If anybody is requiring for that purpose, you please let me know, then I will arrange for that visit also.
Future.
You can contact Professor Praveen and he will guide you how to proceed. For biomaterials means it's a implants, metallic samples. Yeah, polymers. If there are insulators, if there are insulators that can be characterized, we can use FIB and we can prepare the samples. But for polymers, usually low kV SEM you can use it. So that also can be done so we have a Professor Bose, Suryasati Bose, who is who have this low kV SEM for characterization.
Metal complexes.
Metal complexes. So these are all in bulk form or it's in nanoparticles or what? Yeah, bulk form. So it can be done. It's fine. So we can try for the atom probe tomography and you can reveal, or you can try for the yields where you can do the carbon mapping. That can be done. For the light elements, as I told you, yields and the atom probe tomography is the best. So depending upon the sample, either of the techniques you can use it. In SEM we have a temperature controller. We can increase the temperature till might be around 600 or 700.
Do SEM image, but I want to take that to 180 degrees.
Yes, it can be done.
In cooling cycle.
In cooling cycle also can be done. We have a heating stage, special heating stages. Even we have a heating stage in TM, which can go up to 900,000 degrees Celsius. So if you have a TM sample, then we can use the microscope at high temperatures. Samples, that main rectangular samples are used for the TM. So these why I usually I will prepare needle specimen is I can use the atom probe also simultaneously. But from the TM samples also we can prepare the APT needles. It's not a problem. So once you finish your TM analysis, if you have a specific location, then we can prepare the atom probe needles and we can analyze it.
Laser ion beam current, right? This is same as in the case of electron beam also.
Yes, electron beam.
Also, can you explain how it works for nano range and micrometer range, these two beams, in the case of ion?
Yeah. So if you have a larger beam, if you have a larger aperture, you are passing more electrons towards into the aperture and you are collecting more electrons. But you have a lens system where you are converging those electrons to a beam, correct? So there is a convergence angle. So usually in SEM, most of the SEMs they converge it, but it is near parallel. So only the probe size depends upon your that aperture size. So if you use a very small aperture, actually what you can do is your interaction volume also will reduce. So if you have a sample surface which is having some nanometer particles, few nanometers, then it is better to use the low aperture so that so I think Professor Chandan must have explained how rastering is happening. It's a pixel process, correct? It's a pixelated ion beam also. It's a pixelated. So it depends upon your so your magnification is the scanning region plus that pixel. correct, divided by that pixel. So these are all correlated with that. So if your probe size is less than the pixel or near to the pixel whatever it is there, then you are getting the correct information, you are not getting from the other region. EBSD is for the diffraction, EBSD, electron backscatter diffraction. Elemental mapping you can do in SEM, you can do in TM also, both.
So basically for nanometer region, we will use smaller beam, right?
Smaller beam or the smaller voltages, you can reduce the voltage also, so that your interaction volume gets small, so you will get more accurate information. Ultimately, if you have two particles which are very nearby, you don't want to overlap the their information, correct. So for that purpose,
No, in electron beam, that same electron beam elastically it will give a secondary image, no? Secondary
electron beam.
Yes, the secondary electron it will give.
Secondary
Same
electron.
it will
Correct.
reflection will give. In
Correct.
ion beam, how it will give secondary? You are using ion beam.
yeah, I am using ion beam. It is bombarding to the atoms which are present on the surface. From those surface atoms, your electrons will come out. They are all secondary electrons, correct? Yeah, it's fine. So see the terminology as from electron beam, these are primary electron. See, always primary means the incident. We are not using primary electron in the ion, field ion. But as per terminology, those are called secondary electrons. Then you are correct, that's fine. Yes, if you do the in a definite crystallographic direction, you can get the structural information also.
Once again. We have some guests today with us. As I was telling you in the morning, we have iSTEM. I think many of you are aware of iSTEM. This gives you a very nice window to book equipments from all around the country. And with us, we have Dr. Harilal Bhaskar. He is the Chief Operating Officer of iSTEM, and also Mr. Manjunath, who is here with us. And they will give you a short introduction of iSTEM and how can we use this portal to book, let's say, various equipments, I think particularly XRD at IISc. Yes. So, please. So, can he use your laptop? He has a pen drive. Oh, yes. This one. Yeah.
Am I audible? Good morning, all of you. First of all, thank you so much for IISc leadership for providing us an opportunity. I don't know how many of you heard about iSTEM. Just want to, just see that first. Oh, at least I can see 4 to 5, hands here. Thank you so much. Of course, Professor will head about it. I know you've been trained on XRD and SEM from IISc, professors in the last few days. But how many have a challenge of accessing an equipment inside IISc or IIT or any of these premium institutes in India? For example, you want for your research to do, but where you find a challenge to access this equipment because its institute is very near to you, but entry to the institute become a challenge for you. How many of you? Can you just raise any hand on your personal experience? I think 2 of you have really, so you are into PhDs or doing PhD or something? IISc itself? Oh, so okay. So you try, you want to have a access and equipment, but you have a challenge of reaching out the institute and other thing, right? Okay. So Government of India, of course, think about it, right? So the Office of Principal Scientific Advisor, Government of India, has conceived a concept called aggregating all the research equipments or research infrastructure to a one platform. That is called iSTEM, Indian Science. So you can see the complete, just next slide. Yeah, sorry for that. So this is all about ISM. Again, I said the Office of Principal Scientific Advisors is conceived and funded, and this idea is like a national research map in terms of what are the equipment available, including IISc. We have a lot of equipment. We may already talk about some of the equipment, how to access, to talk to the professors, right? So, but it's easy, like you booking a bus ticket. Red Bus, there is a platform. You can book any of the bus running from Bangalore to any other part of India. That's easy. Like you can look at availability of the bus and then you can book it. Similarly, through ISTEM, you can look at any of the equipment available in IISc or any other institute in India, like Raman Institute or any other institute like IIT Delhi or IIT Mumbai. Wherever it is, you want to book an equipment, you can search it, see the availability, and then you can book a slot for the equipment. I'm not going to the basic thing. I just want to give a little statistics, how many equipment we have and how many institutions are in our portal, and then also how many of the researchers already reached out and how many experiments we conduct. If you look at here, we have around 30,000 equipment we listed. We are growing. Actually, this may be a little bit of old statistics. Every day we are adding more in equipment, and then we have around 3,741. Maybe in India around 10,000 plus engineering colleges are there. Out of them, maybe 5,000, maybe near to that, actually having a sophisticated equipment. So this is a pretty good number. You can see that around 3,741 students are listed, and then we have around 48,000 plus researchers already access our portal and book the equipment. That means they use the equipment through our portal, and 74,000 requests made it, and then 36 out of that fulfill. Why actually you see the 50% down here? Because sometime you may request it, you yourself may cancel it. That is the one possibility of number reduce. And otherwise, you book for an equipment where you want to be maybe next day for the same institution, but operator is not available, it's completely overbooked, then of course you may not get it. So various, in any case, you get a proper communication to the ISTEM portal. You can communicate with the operator, you can understand what is the problem there, extra. So you look at the distribution. This is very important. We have, of course, the focus is tier 3 and 4 cities in India, because in like tier 1 city like Bangalore, you have a lot of institutions including IISc and including even CCAMP and all other things are nearby to you. It's easy for you. But somebody from Karnataka, say example like Karwar or Madikeri, they don't have much access. So what we are doing is actually we try to spread the news about the available equipment to the rural area. So, and then we see that the drastic change, like tier 1 and tier 1 actually, if you look at here, actually 19.7% are from tier 1, but if you compare to other tier 3 and 4, others means tier 3 and 4 together. And then the good thing is like we are catching up in terms of gender distribution. 40% of the ones are still using it, but of course we try to catch up doing various programs for the women empowerment. Like we did a program called Nari Vidushan program, where actually women researchers were reimbursed for the expense where they access the research. And then we also had a program with AICT Aura program, where actually they supported the researcher by once you use the lab, you can submit your invoice, then AICT will reimburse you if your institute is an AICT approved one. So I'm not going to a lot of statistics, maybe not interesting for you, because I will brief quickly and then I will get into the portal. We also request my colleague Manjunath and my colleague Rupalim, she is a marketing manager, and my another colleague Namdeshwar Pandey, that is a SME manager, will quickly brief through actually the process. Especially Manjunath have a lot of things to say that how to register on the portal. And then finally we want to see it you again whether you registered, because it's a national portal under Government of India. You must completely utilize the opportunity for that. So I'm not going through all of this slide. So I'm getting to another slide where I will start show you some of this detail. Then my team will take over. Yeah, there was a program called AICT Aura program in the last year, 2025, and where actually the AICT, chairman, Mr. Sitaram, actually announced something along with us. Suppose you use an equipment, example IISc, you use an XRD in the lab, and then you generate your invoice, maybe institute will provide invoice, and then ISTEM will verify it. Then you submit the AICT, they will reimburse the money. This year they didn't announce, but hopefully by 26 there may be possibility. Last time we have some discussion. Similarly, for a startup, we have discussed with the secretary of DPIIT, where actually startup using the premise for the prototype development, of course, can submit to DPIIT, and then they'll may reimburse the money. I'm not saying that the discussion is on the process, but it was announced last time around 600 plus researcher utilize this opportunity. Sorry for a lot of confusion. Oh, this mouse some issue was there. I have some issue. Yes, sir, not this one, sir. Some issue with the mouse. So you have a clear understanding. Before I get into this, you have a clear understanding. It's like it's all about like rendering. I don't use the word rendering here. Suppose an equipment slot, you want to book it, you can access system portal, and then you can search it, and then you see the availability, and then look for the slot. So 10 to 11 a.m. Suppose you want to use it, then of course public user. Then you can go to the lab. One way is go to the lab directly. Second is you can send the sample. Suppose you are a chemistry researcher, your sample is ready, you want to get it done by IIT Mumbai. So example, you can send to IIT Mumbai, and then IIT Mumbai's operator will help for you, and then you can use that. See, if you look at here, this is a national portal, IIStem. You can Google it, www, or just say IIStem in the Google, and then you can go to the www.iistem.gov.in, and then you can see this portal, where you have a search equipment, and then you can select the city, and then finally you can do a search. Or you can also have advanced search. We'll show in the next window. But before that, you have to register as a user. When you want to register as a user, your basic detail need to be filled up. Right, as a researcher, which institute you belong to, why your institute is very important. Suppose you are a IISc, and then you want to use IISc research equipment, then of course you treat as an internal user. Suppose you are actually registering as an IISc researcher and using IIT Mumbai's equipment, then of course you are an external user. They have different charges, maybe apply from the institute. And then of course you can look at your other detail, like which, as I said, academic information, and then research area. If you want to do it, you can put it across, and then you can search equipment here. I'm going a little faster because my team actually explained you in the detail, because we have a time limit of 20 minutes, but we have all videos and then demonstration available across it. 5 minutes? Okay, then I'll just go for faster, a little more faster. Yeah. So if you want to, if example, like when you book a train ticket, you get actually PNR number. Right. Similarly, here there is a number called FBR number, facility booking record. This number actually can use for your any kind of escalation question to the operator, or maybe if you want to talk to the institution why this my equipment request is not fulfilled. So yeah. See, this is a search of an equipment. Then suppose you are putting XRD. You put it, write it here, XRD. Then all the XRD nearby you will show here on this list. Then you click on one of them, you see more detail on the right side, right? And then this is a test equipment. See, you see the test equipment right side, where actually see XRD in Indian Institute of Science. Then you actually see the detail of the equipment. Then you see the all these detail right now, where all these material samples, what you want to provide it. Then more detail, like maybe some of the sample per liter, some of them are per sample. All the detail you can give it. The price also, what are the institute providing, and then you agree on terms and conditions, because we say we are just a facilitated platform. We have to follow. You can't contaminate the lab. So there are rules for you to make sure. And then once you see it, you book the information, finalize it. You select the date here, and then you put the slot, which time you want to book it, and finally all the information you push it. Finally, this example, verify the booking information again, you ask you, then you are done. And then you generate an FBR now, PNR number. This PNR number is for your reference. It will reach your operator. Then you can have a discussion with the operator to understand what you want to take care of, your sample need, this kind of preparation. All this instruction can be given. And then that's the way it should happen. So I'm just summarizing these my colleagues here to explain some more other details, because we have time is also limited. So any question? What we have is we have a YouTube channel with all the languages now. We are starting with around 5 languages: Kannada, Tamil, Malayalam, Hindi, and then Bangla. All the languages available for the demonstration, just for supporting rural people, not only for you, maybe all of you can understand English, but I'm saying we have to support the rural innovators. That's a major reason. And then we have a detailed description of user manual. We also have one-page manual, or you can say how to book all the equipment, right? So this will actually, my colleague is in the here, and they will explain you more. I'll invite Rupalim first, and then she will explain in actually some of the thing, opportunity for you as a researcher. Yes, Rupalim, I welcome you to give a, sir, 3 minutes. We have some program called.
We are running really tight on schedule.
Oh, is it so?
Yeah, because 1:30 next session will begin.
Oh, okay.
For that we must have coffee.
So 2 minutes. She will explain about ambassador program.
Yeah, as effective as possible.
So for thank you. Thank you so much, guys. So anyway, we'll be here. We can reach out after this.
Good morning, everyone. I promise that I won't take much of your time. Just like Dr. Harilal has already explained about ISTEM, and as researchers to meet the challenges during your research journey, please visit the ISTEM portal. Go through our social media channels. You will have a lot of resources on how to register, how to book the equipment. We also have weekly demonstration sessions to help you, guide you through the process as well. So do follow our social media channels, go through the YouTube channel. That will help you a lot. Apart from that, 2 things quickly I would like to, present here. For researchers, for, PhD scholars, and for anybody from the STEM field, passionate individuals, we have this program called Ambassador Program, ISTEM Ambassador Program, which is basically a voluntary initiative to integrate into you into the research and development ecosystem. So that is how passionately you can integrate yourself in carrying forward the ISTEM objectives. So you can write back to us, and if we find you fit, we will include you as one of the ambassadors, where you can help us build the community. We also have the different type of events, where one of them is the operator training program, which is basically different institutions with their high-end and sophisticated equipment, they train not only the operators but the researchers as well, or the students, on how to use those equipment for their research. So these are the different kind of details which you will come across if you follow us, if you go through our website, and we would be happy to help. So please reach out in case you have any kind of query, you want to associate with us, you want to attend these programs, we would be happy to help. Thank you so much.
And also today we have already distributed these pamphlets. Those who are going to register today itself, we will give one goodie type of maybe t-shirt kind of thing. So by end of the day, kindly register through ISTEM. Thank you.
Okay, thank you so much, sir. Thank you. Appreciate your time.
Thank you very much.
We'll meet you again sometime.
Yes, we also get so please, I hope that this was useful for you because this opens window to many equipments. So please use it. It will be helpful. So anyway, now let's have some coffee and we will meet again at 11:30. So it's a little short coffee break. So please join the speeches. The end of the lecture, and that will be given by the next lecturer. You already know him. And today, I think this time we will talk about the spectroscopy. Then we do a lot of interesting things using SEM itself in terms of the chemistry, and he will guide you. And we'll see if we don't have time, let's say at the end of the lecture, then we will go for the lunch, and then soon after the lunch we will do the certificate distribution, and then we will follow the okay, so we will play by the ear. Okay, thanks. All right, so now we will get started. Raise this board.
Hello. Okay, so we will proceed with the okay. So now today I'll mostly be using board because it is easier to understand on board. If I keep showing slides, then it doesn't really help. So we'll proceed. So I hope yesterday you saw SEM and you were able to see some of the knobs and magnification and so on. So today we'll worry about the spectroscopy. And one is EDS and WDS. EDS is energy dispersive spectroscopy, and this is wavelength dispersive spectroscopy. Okay. Now there are two ways to characterize a material. Okay. Now if you or there are several ways to characterize a material. So suppose if I have a material like this, then the one way to characterize the material is its shape, size, its roughness of the surfaces and so on. So by looking at it, I can say that okay, this is this shape, the size is this much, and this is a smooth surface or a rough surface and so on. But you cannot really know what it is made up of if you don't do any kind of analysis of the materials. Okay. So the vision, okay, in some cases the vision can help, because if you can know that if it is of a gold color, then it most probably is gold, or I mean it is white, then it is silver and so on. But to know exactly what it is, you need to probe the atoms in a certain way. Okay. And yesterday when we were looking at the interactions, then there are two kind of interactions we saw. One is the elastic interaction, another is the inelastic interaction. So elastic interaction and inelastic interaction. Okay. And so the elastic interaction will give you what it will give you. Can you still remember, or you forgot? Backscattered electron. Very good. It will give you a backscattered electron, and the inelastic scattering will actually give you a secondary electron and X-rays. Okay. And the X-ray is basically emitted out from the material. Okay. Now so if you draw an atom, and let's just call atom A, and this atom basically has electrons and nucleus, and one electron is coming like this, and if it is not interacting with the atom and it is going out, then it is BSC, the backscattered electron. Okay. The change in the direction of the electron happens even if it interacts. Even if it interacts to strike out a secondary electron, there is a change in the direction of the incoming electron. Whenever there is change in velocity, which is velocity also has a direction and the speed, the energy of the system changes, and this change in energy is manifest as some other X-rays which are given out. Okay. And this X-ray, let's say we call it X-ray also, but it's called background. So in in the event of BSC, when there is a change in the direction of electron, or in SC when there is a change in the direction of electron, we also get X-ray. And now we also saw that what is the mechanism of generation of X-ray, which is also in the XRD you may have heard. So if there is an electron here, and if there is an incoming electron which hits this electron and this electron goes as secondary electron, then there is a vacancy here, and to decrease the energy, an electron can jump from here to here, and that gives out a X-ray. And this X-ray is called a characteristic X-rays. Why? Because the way the God has made the world is that no two transitions will have same energy. Okay. Now, let us just see how do we quantify this X-ray. Okay. Now, to quantify these X-rays, there are detectors which are present, and these detectors work on a simple principle, and that principle is this, that if you have a PIN junction diode, so this is intrinsic region, this is P region and N region, and this is reverse bias. Okay. Then there is no current flowing in the circuit because it is reverse bias, and if this X-ray which is emitted here, this X-rays goes and hits this point, then it will generate electron hole pair, and this electron hole pair will now transfer through this thing, and that it will read a current, and the value of this current will be proportional to the number of electron hole pair produced, and the number of electron hole pair produced will be proportional to the energy of the X-ray which is hitting the detector. Okay. And in this way, by measuring the current, we can measure the energy of the X-ray, and hence we can know the atom chemistry. Okay. So, in broad way, so you measure the current, and that current is proportional to the number of electron hole pair, and which is proportional to the energy of the X-ray. Okay. Now, this is we are talking only about the principles involved. We will talk about how the spectrum looks and so on. How many people have seen an EDS spectrum? Okay. So, if so, you saw it EDS spectrum yesterday, right? Okay, very good. So, so the EDS spectrum looks something like this. I will draw again. There should be a duster around. Metal, okay, and you take that copper metal, and if you put it in the chamber of the SEM which you have seen yesterday, and you let the electrons fall on the copper, okay, and if you let the electron fall on the copper, then it will generate secondary electron, backscatter electron, it will also generate X-rays, and these X-rays, this X-ray will have a certain amount of energy. Okay. Now, what happens is that in an atom, if you have a nucleus here and then there is an electronic shells around, and if this is K shell, L shell, M shell, and if this is there is a vacancy here, an electron from L shell jumps to K shell, then the X-ray is called K alpha. This is a notation. Okay. If the electron jumps from M shell to K shell, then the X-ray is called K beta, and L alpha and L beta subsequently, when the if M to L shell, then it is L alpha beyond N. and all these energies basically are certain distinct energies. So, if I make a plot where this is the energy of the X-ray, okay, and I take, let's suppose I take this energy value, I just pick a number and I call it 3 keV. Let's suppose I just have picked the number, okay, and I make a, I call this as 3 and this is, let's say, keV scale. Then you will have some activity at this, in this plot at 3. What is that? You will be seeing a peak, and this is counts, and this is energy, and this is corresponds to copper K alpha. So, if I am, so what it is actually doing is that the detector it's like a it is like a box with a shutter. Imagine it this way, and it has that shutter opens and closes very fast, very fast, several times in a microsecond, okay, and every time the detector opens, one X-ray, one quantum or quanta of X-ray enters the detector, and then the detector door closes, and that produces electron hole pair. And then the door opens, the next quanta of X-ray enters, door closes again, it produces electron hole pair. So, if the different quanta of energy corresponding to that X-ray, it is entering one at a time, then every time the number of electron hole pair will be same, right. So, the and that current will tell you the energy of that X-ray, because it is, see, if you take PIN junction diode, you can calibrate it. You keep it outside the SEM, you give it a certain amount of energy, and you measure the number of electron hole pair produced. So, you basically have calibrated it. Now, you have taken that thing and you have put it inside the SEM, and now based on the number of electron hole pair, you know the energy of the X-ray, okay. Now, if I run that experiment for a certain time period, for example, if I run that experiment for 10 minutes or maybe 5 minutes, or let us say 10 minutes, pick a number, then the number of X-rays that entered, or number of the quantum X-rays entered, will give me the number of events that happened in the sample, which will give me the counts. So, the presence of this peak tells me that there is a copper which is present in the sample, and the height of this peak will tell me that this much of the material is, or this much is the interaction volume. It is all copper, so it does not matter that how much copper is present. It tells me that in that period these many X-rays were extracted, right. So, for example, if I it is important to understand this. If I open this door and if I ask one person at a time to go outside, okay, then people who is standing outside will know that there is a seminar going on, because everybody is wearing a ribbon. No students in department will wear that, okay. So, that is established that there is a seminar going on, and in a certain time period, how many of you go out through this door one at a time will tell you approximately what is the number of people would be sitting in this hall, right. So, that will give me a peak. So, this is a typical EDS spectrum which you would have seen yesterday, okay. It is count versus energy. Energy gives me the identity, the count gives me the quantity. Okay. Now, suppose that not only one transition will happen. So, if k beta can also happen, right, the electron can come here to here, it can also jump from M shell to K shell. Okay. So, you will have a K alpha, you will also have a K beta line, and so on. And there can be a possibility that M, if there is a vacancy here, M will jump to L, okay, and that will give me L alpha line. So, the L alpha line will be somewhere here. The good news is that the software does everything. So, you do not have to take much effort in this thing. Okay. EDS is now completely automated, but it is important to understand there can be several ways you can make problems can come here. So, we will talk about it today. I see all of you are very tired. Too much gyan in 4 days. Don't worry, these things are, you have to take it easy. Okay. Don't burden your mind trying to understand things. Okay. Just take it lightly, it does not matter. Okay, fine. So, this is the spectrum that you would see usually. Now, let us work on this spectrum little bit. Now, I told you that this energy 3 keV is a characteristic energy. So, if the energy was 3.1 keV or it was 3.5 keV, will that be a copper K alpha? No, ideally it should not be. If it was 2.8 keV, it should not be. It has to be exactly 3. So, ideally the spectrum should not look like this, the spectrum should look something like this. Because here you are also, this is 3. So, here you are getting also some signal at 2.8 and 3.2, which is an error. Na? So, ideally the spectrum should look like this. In a perfect world, the spectrum, and why should there be a background? There is no use of background, there is only copper. So, ideally the spectrum should be a straight line. You have only copper which is giving out only K alpha, and it has a characteristic value. Okay, but it is not the case. You always see a peak, and we will see why that is so.
Neighboring overlap.
So it does not have a neighboring, so that we will come to that. It might have a neighboring overlap, but we will come to that. But what you actually see is, you actually see something like this. Okay, and the character of this is defined by a background. So this is a background, and there is a width associated with the peak, and all this background and width are basically errors in the spectroscopy. But what is the origin of this error? The origin of this error is basically because of 3 important factors. One factor, why you see a background? Because when the electron changes the direction, so when the electron which is going at a very high velocity changes the direction, that change in direction is very random. It can change direction anyways if it is not interacting. So, there is a fair amount of chance that it changes a direction such that it gives out 3 keV X-rays because of that change in direction, not because of the excitation of the copper atom, and that creates this particular zone which is the background. So, this is one error. So, there is a background correction one has to do when you are doing the EDS, but good news is software does it. Okay. But this is a source of error. The other part is that, see, when the transition happens and the X-ray is basically emitted, then that X-ray goes and hits a detector, I told you, and it generates an electron hole pair. Sometimes that detector is also man made. Detector also has, let us say, defects in it or something. So, sometimes the electron hole pair generated will be 1000, suppose pick a number, sometimes it will be 980, sometimes it will be 1020. So, the number of electron hole pair generated in each event cannot exactly be 1000. This is just, and then you have the wires which carry the current, the wires have resistance. So, the current which you are measuring will not be every time same and proportional to the X-ray energy. So, the detector electronics which you are using brings in this width to the peak, but we have to live with this width, we cannot do anything about it, okay? Because there is always an uncertainty associated with the electron hole pair generation. There is also, and fundamentally, if you, now I am not a physicist, but fundamentally there is also an uncertainty associated with the transition energy of the electron from the K shell to L shell. Sometimes it can be 3 eV, sometimes it can be 3.0000001 eV, but that uncertainty is not that much, so that it make a sizable difference to the width of the peak. So, in any spectroscopy, instead of getting a line, you get a peak which has a certain width. Now, so you, even if you do now, even if you do a single element, you will see all kind of K alpha, K beta, L alpha, L beta, because there will be vacancies and electrons will be transferring. So, if there is a vacancy in the K shell, then you cannot ask the M shell electron not to jump to K shell, it will jump, okay. So, there will be a family of lines. So, if you say, if you see K alpha, you will most probably see K beta, you will also may see M alpha and so on. So, this is called family of lines. So, this is how the EDS spectrum is defined. Now, suppose that you have two material, you have copper and gold. So, you have, suppose you have a alloy, all the rings and chains of gold that you are wearing are not 100% gold, they have some amount of copper in that. So, if you put those things in the SEM, you will always see more than one element. So, if there are more than one element, then you will see more than one kind of peaks in the spectrum, okay. So, if you have so, you will see a background, you will see more than one peak, and we just for the sake of simplicity, we only take K alpha peak, we ignore the other peaks, okay. And this is copper K alpha and let us say gold K alpha and that is how you actually know that there are two elements in the sample, okay. But the question is that how much of those elements are present, that we have not still come. I am trying to tell you that the spectrum here tells you that there is a copper and there is a gold in the sample. Okay. Is there any question till now? No, that is fine. Then we will move forward. Now, suppose that you have you know this already, and so you suppose you have a friend who comes and tells you that I have this material with me, suppose this material with me, can you tell me what are the elements present in it and how much of those elements are present in it, and he gives you a solid block of metal. Okay. So, what will you do? You will first go to the nearest SEM, and if you put that block inside the SEM and then you hit some buttons, you will generate a EDS spectrum, and that EDS spectrum possibly will look like this, suppose. Okay. Then you call your friend and you tell that, oh, I have found out the block that you gave me has copper and gold in it. Okay. But the question is that the person asks you that that's fine, but can you tell me how much copper or how much gold is present? Okay. So that thing still remains. Okay, fine. So quantify. So now what you do is that you now know that, okay, fine, there are copper and gold is present. So what I will do is that you go to the nearest market, you take your bike or car and go to the nearest market and go to a jewelry shop and tell that jeweler that you give me 100% gold. You don't worry about making jewelry, you have some gold block, you give me that, I want it, and you bring it back to your SEM. Okay, and you put that gold in the SEM and then you switch on the machine. Now you will get another spectrum. Will that spectrum be same or different? It will only show single peak. Very good. It will only show single peak. That single peak is the gold peak. Okay. So let's draw that spectrum. So we'll draw it here only, so that we'll do a makeshift thing. So this peak will vanish and you will only see gold peak. Now you will calculate the area under this peak, okay, and then you know that, and suppose I draw another peak. So for the pure gold peak, you will see a peak like this. Suppose the red one, you calculate the area under the peak and then you try to do a math, and that math is that if I have 100% gold, okay, then the area under the curve is, let's say, C1 or C standard. Okay. And if I run my friend's sample, and if the area under the peak is this blue peak, area under the peak, then let's call this as C sample, and that should basically solve for X, and that should give me the amount of gold which is present in the sample. Very simple. Okay. And then you find out that, okay, this number possibly, let's pick a number, this number is 40 atomic percent, and then you call your friend who is a microscopist, unfortunately, and then you tell him that I have found out it is 40. Then the person says that no, it is not correct, it is approximately correct, but it is not 40, it is 50, suppose he says. Then he asks you about the things that you have done, then you describe it, and then he asks you a very important question. He asks you, have you run the microscope under similar conditions for the two experiments? Okay. Then you start wondering, have I run the microscope under similar conditions? Okay. So let's write that phrase. have I run the microscope under similar conditions. And this is important, because you can only compare two events when the, and you can use this nice simple equation if both the events happened under same conditions, exactly same conditions. Okay. If that is not the case, then this simple equation is not valid, but let's make that, let's just look at this phrase little bit. Now, what is practically happening inside the microscope? Electron is going and it is hitting the sample, okay, and all the circus happens when that electron hits the sample. Okay. Now, let us take that thing. So, if this is a sample and there is an electron hitting the sample, then what are two important characteristic of electron is basically, one is the energy of the electron. Okay. So, energy of the electron, and other is the number of electron which is hitting the sample in a certain area. Okay. These two things are very important, and number of electrons which are interacting with the sample, and this interaction volume basically is something that is. Now, the energy of the electron, how can you vary the energy of the electron? By changing the acceleration potential, that is called kV, accelerating voltage in a machine. If you go, there is accelerating. So, you tell your friend that no, I actually kept the accelerating voltage exactly same. Okay, very good, he says, and then the number of electrons which are falling on the sample can also be controlled. How can that be controlled? By using aperture. Very good. There are apertures in the way. So, the electron comes like a shower, and by using a certain aperture you control the number of electrons which hit the sample. So, you tell your friend that yes, I am very careful person, I have never done anything which is not same. This was same kV, and the number of electron was also same, because I kept the aperture size same. Okay, that is fine, but there is a problem here in the sample, because fundamentally a gold copper sample is different from a gold sample. So, the way the electron will interact with the sample will also be different, and that is where you do not have any control, and that is basically is called a ZAF correction. If you, so this equation can be rewritten by a certain way. I will write that equation, then I will explain you about it. So, this equation, the correct way of writing that equation is C by C standard by X is proportional, not equal, is proportional to the intensity of standard by the intensity of sample, and that is the integrated intensity area under the curve. That is proportional, that is true. Okay. and the proportionality is always removed by a constant alpha, and that alpha is basically called ZAF correction. And I standard by I sample. If you go to the textbooks of spectroscopy, these are mathematically extremely complicated formulas you will see, but I will tell you the physical meaning of this correction, okay, which is something that you should realize. Okay. So, what happens is that in the interaction volume, when there is a pure gold and when there is gold copper present, is the average atomic number different between gold and gold copper? Yes, it will be different. No? I mean, if you take an element A, pure A, and if you take an alloy of A and B, which A and B have different atomic numbers, then in a certain volume the average atomic number will be different. So, the number of when the electron comes in, what happens is some of the electrons are turned out and they are lost because of the backscattering, and this backscattering will be different in gold and it will be different in gold copper, simply because of the fact that the element atomic numbers are different in this alloy or this is a pure metal. So, suppose 100 electrons are coming, and let us not worry about, let us take A B alloy, where A atomic number of A is very high than atomic number of B, and this is B element and this is AB alloy. So, if 100 electrons are coming down and hitting the sample, if the pure element loses 20 of those electrons by backscattering, and if the alloy loses 50 of those electrons by backscattering, then the number of electrons which are used to produce the inelastic scattering event, are they different or are they same? They are different, isn't it? If I ask 10 of you to go and break that glass there, I always want to, or if I ask 20 of you to go and break that glass different, the havoc will be different, right. So, and which kind of electron is what interaction is creating X-rays? Inelastic interaction is creating X-rays. So, the number of electrons which are doing the job is not same. So, if I have 100 electrons, see, if you keep kV same and you are keeping the number of electrons same which are hitting the sample, that is true, but once the electron hits the sample, in one case 50 of them are not interacting, they are just going as backscatter, and only 50 is doing the job, and in one case 20 of them are going as backscatter, 80 is doing the inelastic scattering. So, there is difference in the number of electrons which are doing the scattering event, and that simply means that the two samples are not seeing the same number of electrons, even though you are putting the same number of electrons on the sample, but inside the sample the job is done by two different numbers of electron because of the loss of electron because of backscatter. So, that is a difference in the condition, and that difference in condition is not user controlled, it is sample controlled. So, if you have uranium and if you have tin, which one do you think will have less number of electrons doing the inelastic scattering? Uranium, because it is so heavy that it will turn most of the electron out as backscatter. So, so what happens is that in the software, now there is a mathematical formula. So, the mathematical formula, what it does is that you tell the computer that okay, I am expecting gold and copper. You will see peaks, then you identify those peaks. The computer mathematically forces those number of electrons in the sample and causes that event to happen, right. So, for example, try to understand if you understand this, then you are actually through. So, in one case 50 electrons are lost by backscatter, 50 electrons are generating secondary electron and X-rays. In other case 80 electrons are generating X-rays. So, the computer, but the condition to be same, both should have 80 electrons or both should have 50 electrons, right. Then only you can make a comparison. So, when you identify the peaks, the computer has this mathematical formulas which in any textbook can give you. Computer adds those number of X-rays into the total number of X-rays which are plotted here. So, if this count is, let us say 30, the computer knows that okay, it does all these Monte Carlo simulations and it knows that the sample would have only 20 less electron than the standard, and these 20 electrons will produce 200 X-rays. Then the computer mathematically adds that X-ray into this, it raises this peak mathematically, because that is the way the nature is, and that correction is called a atomic number correction, which is called the ZAF. Z is the atomic number correction. Okay. Now, the second correction is the fluorescence correction, sorry, absorption correction. And absorption correction is very simple. You may have also in your normal physics and 12th class you have seen that when X-ray passes through a sample, okay, it can get absorbed. Okay. So, if the interaction volume is, suppose this is the interaction volume and X-ray is produced in all over the interaction volume. So, I will draw here. So, X-ray is produced here also, here also, here also, here also, here also, here also. Okay. There is a possibility that this X-ray while going out gets absorbed in the material, because of which we lose the. So, suppose in the total interaction volume 100 X-rays were produced, that would determine the height of this peak, but the absorption coefficient of that material is such that 30 X-rays are absorbed. Then how many X-rays you are actually seeing? You are seeing 70 X-rays, but so that means, and suppose in a very simple world one atom produces one X-ray, then your computer will tell you that there are 70 atoms of element in the sample, but are there 70 atoms? No, there are 100 atoms. You are using X-ray to know the number of atoms. If those X-rays are absorbed, then your count is wrong. So what happens is, then you give the computer the information that okay, my acceleration voltage is 20 kV, my spot size or number of electrons is n, and my material is made up of A and B elements, and from this the computer would calculate the interaction volume by simulations. And then the computer will also calculate that how many X-rays will get absorbed, and it will mathematically add that X-ray into the intensity. Okay. And that correct. So if the intensity is coming here, then it will add or subtract also sometimes, but that subtraction is a little complicated, let us not go into that. It will add those many X's, and that correction is called an atomic number correction, absorption correction, sorry. First is atomic number, A is absorption correction. Okay. And the third is basically fluorescence correction. So, the fluorescence is something like if these two peaks are very near to each other, okay, then the energy of one X-ray can be used to excite the other element. So, for example, if you have two peaks like this is gold and this is, let us say, some we pick a element, let us say B K alpha, and this is gold. So, this B K alpha, when it is going out, it has the capacity to excite, knock out an electron from the gold K line to excite this X-ray. So, then it will be lost to this excitation, and that would actually lead to an error. So, suppose that so it is like this, that if a one X-ray is travelling out and if that X-ray has a certain amount of energy which is very near to any other excitation it can cause, and once it sees that atom, it will get absorbed and cause that excitation. So, this peak, even though this peak was actually really present, but this peak will go away and this intensity will increase, but this peak is important, it was there in your sample. You lost this peak because of the excitation of this element, and that is called the fluorescence correction. So, the fluorescence correction most probably is less than 1 into the product. You have to bring the intensity down to make this go up. So, these are the, so this is atomic number correction. Atomic number correction is that number of electrons doing the job should be same. The number of electrons which are lost due to backscatter must be mathematically added into the total pool of electrons which are doing the job. Absorption is very simple, X-rays are absorbed by defects and so on. So, that absorption should be corrected, and X-rays, so in fluorescence correction, if there are peaks very near to each other, then you will have those corrections where some of the X-ray which can excite other element get absorbed. So, now when you call your friend and tell that I have done everything and now I give you X standard CAF into I sample by I standard, and then you call your friend and you tell the friend that now I have done so much effort in finding out the composition that you have to give me some money, then only I will tell you the number. So, now it is correct. So, what happens is that, so now you are running the experiment under similar or same conditions. So, now the EDS will give you, okay, the sample has copper 50% and gold 50%. The bad news is that it is still inexact, but we will see why. The good news is that the math is completely now embedded in the system. So, when you go to an SEM, you get this curve and that throws this number on you, and you do not realize that the amount of maths and amount of simulations which are going on in the computer are enormous to get to this number. Okay. But nowadays it's not really very difficult. The system is, the calculations are all done already. But this is called ZAF correction. But there is some element of problem here again. The element of problem, that is, I will tell you, because when you read paper and if you happen to write paper, you will know this thing. That I told you initially, there is a width associated with the peak. This peak, basically, if there is a gold copper, let us get back to, ideally it should be a straight line, but there is a width, and this width is the problem, it is an error. Okay, because you are reading some energy here also, you are reading some energy here also, you are reading some energy here also, and here also, and so on. But you do not have any control, you have to live with the detector electronics, you have to live with the way the world is made. So, in a typical SEM, the numbers should always have a 5% error to what you are seeing. So, if you are saying that something is 50%, then it should be 5% of 50 should be the error. So, the gold is not exactly 50%, but it is 50 plus 2.5 minus minus 2.5 or plus 2.5. So, either it will be 52.5 or it should be 47.5 or something like that. Okay. So, that element of error is there because of the peak width. So, many a time somebody will tell you that I have used SEM, I have seen papers, and I always very uncomfortable reviewing those papers. People will say that I have made 5 powders and the compositions are like this: copper 2%, copper 3%, copper 4%, copper through 2.5%, and I have measured it with SEM EDS. It is not correct, because you cannot really, you have to have a sizable distance between the numbers. So, you cannot say that I have made one sample where element A is 1%, 1.5%, 1.7%, that is not correct. They are all same. So, but you can very comfortably say that I have 5%, 10%, 15% and so on. Because of these corrections, the peak width and so on. Okay. Now, when you have you yesterday when they showed the EDS, what did they show you? What did this? They must have clicked a button. Sorry, huh? Detector came, correct? It was showing some
extra elements like titanium. Low atomic number elements. And she deleted all those elements relative to the atomic percentage. She eliminated. After eliminating all these stuff, and she got 100% of 13.
Okay. Did you ask her why did you eliminate?
It's relative.
Okay, see what happened, I will tell you. That's why we have actually come to the very right kind of discussion. Good that I asked question. See what happened is that the detector is a physical equipment where the shutter opens, the X-ray enters and the shutter closes. When you have only a single element, let us say copper, for example, I am just picking copper, I can even pick nickel, but let us suppose copper. You know why copper is very important? What is very special about copper? Why not nickel? Why not iron? They are all conductors. Huh? It comes in the same league as gold, silver, platinum in corrosion resistance. It is very, very noble. Not noble as platinum, gold and silver, but it is much higher corrosion resistance than any other metal. Therefore, it has conducting property, it is abundantly available, it is also very highly corrosion resistant, but that is a different thing. Let us get back to the discussion. Suppose you have copper and I am copper X-ray, okay, and this is the detector window, and I will window will open, I will enter and I will get myself electron hole pair will generated, I can know the current and then I know the peak. If I am only the copper, I can basically keep entering one at a time, but suppose that if this window which is closing and opening and one X-ray is entering, ideally, if the number of X-ray produced is very huge, for example, and this detector is bombarded with X-rays. So, there is a possibility that when the door opens, 2 of the X-rays will enter. If 2 X-rays will enter, will the amount of electron hole pair will be double? One X-ray will create electron hole pair which is, let us say, n, 1000. The 2 X-ray if accidentally enters, it will produce 2000. The computer will now detect a current which is double, and the computer is not a human being, it will just produce another peak here. It will just double the energy. So, if this, so let us just so if this was copper K alpha, and suppose 2 of those copper K alpha enter, this is 3 keV, it will produce another peak as 6 keV. The computer does not know whether there is element of 6 keV or not, it just measures a current and it produces a peak. This is an error. So, if the person who is doing the SEM is bombarding the element with electrons, if the number of electrons hittings are very high, that is called counts, CPS, it is called CPS, it may have shown you CPS counts. If that number is too high, then what happens is you will start to see many different, it is called sum peak, it is an error, it is called sum peak. And it gets extremely funny and complicated when you have 2 elements. So, if you have 2 elements, let us say gold, this and this X-ray can also enter together, and they will add to produce another sum peak, and you will start to see elements, and you will tell the computer, show me the element. It will use a chart, and he will tell you that, okay, you not only have gold and copper, you also have titanium and zirconium. But you do not have titanium and zirconium. It is just that the sum peak errors are coming, and it is a very common error. So, now there are 2 ways to deal with it. One way to deal with it is that you run the EDS at, now have you heard about spot size? Yesterday we saw spot size. Spot size is basically number of electrons which are proportional to the number of electrons. So, if you keep the spot size little lesser, then you basically have to, you can reduce the number of events, and so if you bombard your sample with electrons, you will start to see these erroneous peaks. Then what you do is that you reduce the number of electrons by changing the condenser lens current. You will do it eventually. When you do SEM, you will do these things. It is just that today you may not catch it, but if you change the spot size, you change the number of electrons, you change the number of events, then these peaks will automatically vanish. If this was actually titanium and zirconium present in the sample, they will not vanish, they will stay. But if this is a sum peak, then the number of, if the number of events, inelastic events decreases, this one will vanish. So, when they, when next time when you do EDS, and if the operator says that no, these are some peaks which we do not have elements, you just ask the operator that can you decrease the spot size, and if the peak goes or not. Okay, so this is an error that you are getting. This is a very common error which you should be aware of. All right. Now, there is another, if you go on the SEM notice again, there is something called dead time. Dead time. This you will see on the detector window. I do not have a photo here, but you will see it here. So, you will see in the computer screen, you will see it will show 2 numbers when you are doing EDS. It will show counts and it will show dead time. If the dead time is very high, dead time is defined as the time when the detector shuts itself off. So, if the dead time is 75%, that simply means that 75% of the clock time the detector is not working. So, if you say that I want to do EDS analysis for 10 minutes, okay, and if your dead time is 75%, that means that 75% of the time the detector is shut. Why? Because the detector electronics has a sensor. When the detector sees that a lot of X-rays are being forced on it, it shuts itself more. So, if there is a 75% dead time, then it simply means that you need to bring down the number of events. So, the rule of thumb is that 30% of dead time is very good. So, 30% dead time and CPS of around 1500 to 2000 and that time of 30%, this combination will give you a good, less erroneous EDS measurement. Now, there is another technique which is called WDS, okay, which is called wavelength dispersive spectroscopy. So, let us talk about that. This is called energy dispersive. This is called energy dispersive spectroscopy, EDS.
You said for copper 2%, 3%, etc. There won't be variation in these peaks, right? So if I have a common with copper and copper 99% and iron is 0.1%, so that 0.1% iron won't cause any peak.
You will see peak, but that peak number will be not. So, if you have a sample which is copper 99% and iron 1%, then EDS is not a good way of. If you are going, this is my suggestion, that if you have anything which is below 5%, then you do not rely mostly on EDS. You can still get a number. It will always give you a number. It will never send you back from it without a number. But the error in that number will be higher if your peak is. See, in any spectroscopy or in anything in the world, there is something called peak to background ratio. So, if the peak is less and the background is high, then the error is high. Right. So, if it is 1%, the peak will be very, very small and the background will be very high. So, the error will be very high. It will give you a number.
So we can't interpret much.
You can just say that if somewhere it is giving 1% and somewhere it is giving 3%, then you can say that the iron is more here and iron is less here. But you cannot say very exactly that it is 1% here and 3% here with EDS. But of course, you can say that it is more here and less here based on the area under the curve.
But from the images we can say that there will be some crystalline development. Even if the peaks won't change much, there will be changes in the same images, right?
See, if there is changing the microstructure or if it is changing the morphology, of course, there will be some change. But I am telling that the exact numbers will always have a 5% error of that number, not overall 5% error. But if you go below 1% or 2%, that actually is a little dangerous. Below 5% atomic percent, you start to get into that gray zone. Above 5 atomic percent, it is okay. And 5 atomic percent means that 5% of 5 atomic percent error, which is 0.25 plus minus. But if you go to 1, then it is very high. So, so if you have very less, let's say 1% or 2%, then WDS is one thing we will discuss now quickly. Other is that you can use atomic absorption spectroscopy or Rutherford backscattering, those things which you dissolve them and you do an atomic analysis. But that's fine. We'll quickly talk about WDS before lunch. This is another technique to determine composition, but it is very simple, and it works on a very interesting phenomenon. Do you know what is Bragg's law? What is Bragg's law? Is equal to n lambda. This is Bragg's law. What is n? Sorry? What is diffraction order? I always ask this question and then people become very silent. What is, like, when you say n is the order of diffraction, then what is order of diffraction? It must be covered in this workshop, right? So if I tell you that usually if I tell you d by n, right? So is there any plane between two planes, by the way, physically? If I have this plane and if I have this plane and there is a distance is d, then what is the meaning of d by 2? Doesn't make a much sense. The problem is that always people bring n on this side and bring it below d. Why? Why don't you bring it below sin theta? See, n is an integer, okay, sin theta is less than 1, so sin theta by n is also less than 1. Let us define this as sin theta dash and we rewrite this equation as 2d sin theta dash n lambda, and now you are actually, you have seen this diagram, no? This is the ray which is glancing the same surface at different angles, and that is the order. So if these two planes are the diffraction planes or planes which are diffracting, and I am a ray which is hitting, let us say, this plane, then I can hit it like this, so making an angle theta. I can also hit it like this by making a different angle. So I am actually seeing the same surface at different glancing angles. I am seeing the same plane at different glancing angles, and that is the meaning of order. There is no such thing as a plane which appears at d by 2. So let us not worry, but this is important for the WDS concept. So now suppose that I have a sample here and the electron falls on this sample, and that will generate a X-ray. And suppose that I have a circle, a physical circle on which I mount a crystal. Okay, and this crystal has known d spacing. So let us not. So Bragg's law, lambda, we remove n, or we consider n as 1. Okay. Now, if this crystal has the known d spacing, is a single crystal which has a known d spacing. Okay. And if I rotate this crystal on this circle, this is called Roland circle, and I measure the angle that this ray which comes out makes with this crystal, and there is a detector here. Now, every time the Bragg's law condition is satisfied, okay, there will be a intensity I can measure here, okay. And if I keep rotating this crystal on this Rowland circle, what I am trying to change, I am changing is the basically theta, and D is fixed in the crystal. So, every time I get an intensity, okay, I know the value of the wavelength of the X-rays. Now, this is pure geometry. See, the sample is giving out an X-ray, okay. All these X-rays have different energies, so they have different wavelengths, and I have ideally a crystal which is seeing the, and it is rotating like this, and there is a detector here which is noting all the constructive interferences, and every time the detector sees a constructive interference, high intensity, I know that what angle the X-ray, a straight X-ray will make on the sample, on the crystal, this angle which is sin theta. D crystal D is already known, and I can measure the value of lambda and the relative intensity. So, once it measure the value of lambda, it has a constructive interference. No, what is Bragg's law? Bragg's law is a measure, a condition of constructive interference. It so happened that Bragg found out, and so he is called Bragg's law. It is a normal constructive interference phenomenon. So, you can see a blink, intensity, right, and that intensity will tell me that the measure of lambda. I can measure the lambda, and how much intense is that is the number of X-rays that are hitting the crystal at that Rowland circle position. This same thing as the EDS, but there what we were doing is that we were using a detector PIN junction diode. Here we are not using any electrical circuit. The X-ray is passing in vacuum, it is constructing interference, constructive interference is happening, the intensity is crossing the vacuum and detector. So, how many wires are involved? Ideally very less, 0. So, all the error associated with the electrical uncertainties are gone. So, if you see the WDS peak will look like this. If the X-ray, if the EDS peaks look like this, the WDS peak will look like this. Which one do you think, the red one will have higher error or the blue one will have higher error? Blue one will have higher error because of the width of the peak, and so that WDS everything is same, all the interactions, electronic interactions, scattering, everything is same, everything is same. The only thing is that in energy dispersive spectroscopy we are using a PIN junction diode, here we are using a Rowland circle with a crystal. This geometry is very simple, if you think about it, it is. And so, what happens is, for example, coming back to her question, so if I have to measure 3%, if I have 3% of iron in copper or 2% in iron copper, then I should look for a WDS machine, and WDS machine is there in the, when you are going for practical, that machine is right before the aprio, behind it. So, it looks little, if you look at that machine, it looks little different from a dabba. It actually is a machine, you will see that there is a Rowland circle, you can, if you look it very close, you ask them that where is Rowland circle, and on which the crystal moves. Otherwise, the ZAF is same, the scattering is same, everything is same. Okay. Now, we have 5 minutes. So the plot is very good. So it is called wavelength dispersive spectroscopy, by the way, wavelength dispersive spectroscopy. So when you go to the detector shines brightly depending upon the number of electrons. So it's just similar plot. The count here is the intensity, and this is energy, which is basically the type of the X-ray or the energy of the X-ray. Okay, that is basically exactly it calculates it determines the X-ray wavelength, and from wavelength it determines the energy. Now, when it comes to WDS and EDS, there is also a limitation. The limitation is that you cannot measure oxygen by or argon by WDS or EDS anything. Why? There is something called Auger electrons. Have you heard about Auger electrons? AUGER, Auger. So what happens is that so suppose that there is an element, and this element basically an inelastic scattering happens, and because of this inelastic scattering, this electron is ejected out. Okay? And there is a vacancy here, and the electron here comes and jumps here, and it releases the K alpha line. In certain cases, if the charge on the nucleus is not very good or very high, this X-ray can kick out this outer electron, and in that process it gets absorbed, and that outer electron is called an Auger electron. So, and this Auger electron emission is very high in all the atomic numbers which are below sodium in a periodic table. So, what happens is that if you are measuring oxygen, many people say that I got 25% oxygen in EDS. So, oxygen K alpha line, some of them will be used to excite the Auger electrons, the outer shell electron of the oxygen. So, if there are 100 oxygen atom present, and let us suppose that each oxygen atom gives out one X-ray, then if 20 of them are used to produce Auger electron, then you will be looking at a 80 oxygen, but that is not correct. And so, if you keep going below sodium in periodic table in Z, then the tendency to emit Auger electrons increases. So, if you are measuring something like argon, neon, oxygen, carbon, these numbers are not correct. You can say that okay, this oxygen peak is bigger in this sample, and in this sample oxygen peak is smaller. So, there is more oxygen present, less, that is true. But if you associate a number that 23% oxygen, that is not correct. So, you have to be careful at that.
We are taking our sample, the carbon sample. So in that part, the carbon peak is more. अगर हम एक्टिवेटेड कार्बन का ही सैंपल हम स्कैनिंग मतलब स्कैन करवा दें तो उस वाले उसमें कार्बन की पीक ज़्यादा नहीं है.
Exactly. So, when you have carbon in your sample, the EDS will show a peak. Okay? Suppose you have only one sample, let us suppose this sample which has carbon, the EDS will show a carbon peak, but if you associate a number that okay, it is 25% carbon, that number is not exact. But if you have this sample and if you have this sample, and this shows a very high carbon peak and this shows a smaller carbon peak, you can very safely say that this has more carbon and this has less carbon. But so, if you say that it is 25% carbon, that is not correct. It can be 22, it can, so most probably you are estimating it lesser, because lot of X-rays can be lost in the Auger electron emission. So, if you are estimating it as 20%, it may be 30%, it may be 35%, depending upon the lost X-ray. But above sodium, you are safe. So, this is basically practically the story of spectroscopy. Uh, the good news is that the computer does everything. So, you have to just go and press button and so when you go and you press button, you get, the computer will give you always a number. Okay. The computer is very honest, it will never send you back empty handed, it will give you a number. now now you, as a scientist or as a user, you have to ask yourself whether this number makes any sense. So, the rule of thumb is that if your the 5% error is always associated with the numbers. Now, this is nobody has written the rule, but in the microscopy community this is something which is accepted, and below sodium do not quantify, above sodium quantify with a 5% error. Okay. But knowing the composition, again you have other techniques also, like you have other spectroscopy method. So, if you have very less 2% or 1%, it is better to use other methods than to basically heavily rely on EDS or WDS, but nonetheless it is the most efficient, fastest and least troublesome method to know the composition. Yeah, so fine. So, slides I will give it to Praveen, Professor Praveen Kumar. If you want, you can, he can pass it on to all the thing, because I think the yesterday's slide and today's slide and all, keep the slide with you, do not upload it anywhere, do not publish it as a book, because it is already from some book. So, do not put it on Twitter or LinkedIn or any social media, it is for your own consumption. I will give some 150 or 200 slide presentation, you can use it for your own purpose. Okay. So, thank you very much, we will meet again. I think there is a lunch there for all of you.
Good morning all and a warm welcome to all of you. I am Dr. Anushka Amle, the field officer here at the Health Technology Assessment Resource Center at the Indian Institute of Science. On behalf of our resource center, it is a pleasure for me to welcome you all to this workshop on health technology assessment of artificial intelligence and digital technologies. We are delighted to have with us an eminent group of speakers, researchers, students, and professionals who share a common interest in understanding how artificial intelligence and digital health technologies can be assessed responsibly to add value to our healthcare systems. The sessions planned for today will take us through the fundamentals of HTA, followed by discussions on deployment and governance of AI technologies, the regulatory environment in India and abroad, the economics of AI-driven healthcare, and finally, the legal considerations in implementing these technologies. Through these sessions, we hope our participants can gain a comprehensive and multidimensional understanding of AI in healthcare. With this, I would now like to invite Professor Sai Shiva Gorti of the Department of Instrumentation and Applied Physics, Indian Institute of Science, and also the Principal Investigator for our Resource Center here at HTA-IN, to deliver the welcome address.
Screen to be projected. Is the mic audible? Like, everybody are able to hear? Wonderful. Very good morning. First of all, thank you so much for joining the workshop, and thanks to the team for putting together an excellent agenda and line of speakers and sessions. All the hard work goes to the Regional Resource Center team, RRC, and the collaborators. So just a minute. So yeah, no, there is no audio. Okay. Later, probably that can be. So, having felt the need for having health technology assessment to be sort of like introduced as well as used more and more in the context of the growing applications of AI tools in healthcare, as well as range of digital health technologies, the team felt that it is important to bring together various stakeholders that helps in gaining understanding about the systematic and evidence-based evaluation, which would help in policy as well as investment decisions in the context of AI-based tools in healthcare, and the need for bringing together the experts from health economics, clinical medicine, engineering, data science, ethics, policy, and to discuss in Indian healthcare context specifically the methodologies, regulatory and practical considerations for assessing how AI-enabled health technologies perform. So in this context, with the objective of the imparting or sharing the principles and the concepts associated with how health technology assessment is performed. So while in other countries, this is more or less has become mandatory, just like the regulatory agencies like in FDA and CE, and India we have CDSCO as regulatory mandatory agencies which govern the the rigorous thoroughness of the interventions and their implications on deployment and usage on the end users. In multiple countries, HTA has already become a mandatory protocol and procedure, and the HTA bodies have been integrated has been integrated into the policy. while it is yet to be really get to that level in India, but health technology assessment under DHR, Department of Health Research, HTAIN has been set up, which is now sharing the policy guidelines with various all the state governments, so that then the governments, especially in public sector, are using these policy recommendations and finding it to be quite useful and helpful in taking decisions on the adoption in the public health system. So the principles and concepts will be shared, and then the discussions on various approaches for assessing the clinical value, economic efficiency, and the system level impact of AI tools. And obviously, this includes sharing insights with the set of discussions and the presentations on the ethical, legal, and regulatory considerations and compliances necessary for in responsible adoption of these AI tools. And this also helps serve as a platform to identify the research gaps and the capacity building needs that exist in the context of strengthening health technology assessment for AI technologies in India. So what is health technology assessment? It is a systematic evaluation of the health technologies for their clinical effectiveness on one hand and the cost effectiveness on the other hand. Not giving more weightage to one or the other. So if there are multiple regulatory approved interventions for a given scenario, like disease or treatment or medicine or diagnostic device or surgical procedure, whatever the process, some may perform all out of 5 interventions, they may have different varying degrees of sensitivity, specificity, and the efficacy and so on. So while multiple things get regulatory clearances, when the government is assessing its tendering the tender process through which they want to select one of those interventions, usually the procedure is to go by L1, whoever is the least bidding, right? So if we do not pay attention to the variations in the clinical performance that these interventions offer and their implications in terms of the downstream expenditure or reoccurrence of the admissions or hospitalization, treatment, and so on, when added, the actual value associated with the given intervention becomes clear. And that is what the QualiGain and IISer are the ones which helps in assessing the value of this on the cost effectiveness of the intervention. So this is important to understand the clinical effectiveness and cost effectiveness. So the subsequent speakers would be throwing more light in terms of how do we give improvement in the quality of life or the value add while considering the clinical evidence. So this is on the evidence-based interventions. So what are covered in health technology? Medicines, drugs, vaccinations, health benefit packages, and guidelines for standard of care, and various health programs, including national missions, which are rolled out, and obviously the medical devices. So range of medical devices, including diagnostics, surgical, and AI and IT interventions. How does this HTAIN works is the usual departments, including the government, public health departments, NHA, and any organization or institution, hospitals, any user department who would like to use these, previously said any of these health technologies may submit a query. It's on website. It can just be submitted anytime, and that goes to, or it can be shared via email as well, to be assessed for its clinical effectiveness and cost effectiveness, and then the value associated with the technology for its adoption. And then that query goes to HTAIN Secretariat operating under DHR, and they assign to the regional resource centers upon prioritization of the technology. And then the regional resource centers and technical partners of HTAIN would then have set of scientists who perform the systematic study and evaluation and conduct the technology assessment, and that technology assessment reports are then submitted back to the technical appraisal committee, and the technical appraisal committee then evaluates both in terms of the proposal, the way, methodology, and research methodology, evaluation protocol, and then once approves, again the outcomes are submitted and presented in the technical TAC committee, and the TAC evaluates it and then enables the recommends for the proceed either going ahead or with the policy recommendation, or in terms of performing the studies, revised studies, or extending the studies to be more appropriate with more data and evidence and so on. And then once the resource center submits back the final report, that gets approved and submitted to the board, and the board finally gives approval, and then it is communicated with all the relevant state governments and shared with the Indian government policy adoption. So there are range of resource centers, so regional resource centers, and while earlier primarily they have been in medical institutions like ICMR associated institutions, of late these are being set up in technological and science institutions as well, like IISc and IIT Bombay started together, and then subsequently it is being expanded in more IITs as well. So depending on each either specialization that the regional resource centers offer or the topics of interest, the topics are assigned for individual studies. So in IISc, this has been set up some 3 years back, and the regional resource center now is operating in the Department of Management Sciences, and Dr. Sumita Gandhi has been heading that. And so we have performed sort of like from IISc, RRC set of studies, and I'll not go through the details of these, and they are all now uploaded on the website of RRC, and you are most welcome to come back or interact, and request you to visit the RRC and then interact with the team. So we have been holding series of these workshops. So the new website for the RRC has been launched, and encourage you to visit the website. And this is the RRC team, and this, as I mentioned before, thanks to the entire RRC team which has put up this and then running things end to end under the guidance of Dr. Sumitra Gandhi, and thank you all. I hope you would enjoy the conference, and thank you for coming forward to share your expertise and knowledge with all of us. Looking forward to have a fruitful workshop.
Thank you, sir, for that address. Next, we move on to the keynote address, which will set the context for artificial intelligence in healthcare in India. It is my pleasure to invite Professor Manish Arora of the Department of Design and Manufacturing of the Indian Institute of Science, who also is the principal investigator of the UTSA lab, which develops affordable and accessible medical technology solutions. Over to you, sir.
Good morning. So, thank you very much for coming to this workshop. My name is Manish Arora. I already gave a brief of my profile. Just want to disclose in the beginning itself that I'm not from artificial intelligence, even though the topic given to me to introduce today was artificial intelligence in healthcare in India. I work mostly in medtech, and with growing evidence that healthcare can get benefits from artificial intelligence, I have been also dabbling a little bit in that space. So, with coming from that background, I would like to present to you the case how healthcare can benefit from it, and what are the precautions, what are the other nuances we need to take care of while working with artificial intelligence in healthcare. Again, of course, the whole workshop is designed around it, so I'll give my views from my limited understanding, but happy to continue the discussions forward in the workshops, other activities down the line. So, just to giving a little bit of background of myself, I joined the institute about 10 years ago, working in the area of, trained originally as a chemical engineer, worked in the applied physics area, worked for medtech company for some time, and then set up this lab at IISc, looking at developing medical technologies, specifically located in Department of Design and Manufacturing, where the goal is to actually productize things. Earlier we were known as Center of Product Design and Manufacturing. Subsequently, we are now Department of Design and Manufacturing, but the goals remain the same, to look at how technology can can be used to generate useful solutions. Specifically in the healthcare space, I believe that health is not only a basic human necessity, but also one can think of it as a human right. Of course, legal definitions might vary, and from geography to geography. But a well-designed healthcare system can save lives, but also have a lot of economic impact as well, for individual family, but also a country, as a nation, or a state, wherever the impact is there. Why did I choose to work in this area? Again, my motivation was that these things matter, and these are systematically complex, technologically intensive, and socially impactful interventions which we are working on. And therefore, it's useful to apply our minds to these things. And being part of the Education Institute training designers, I thought important that designers are aware of unique attributes of medical systems as they're designed. Of course, there are unique challenges in India, and that's why the lab, I moved back to India to work in this area. Those challenges I will explain in the coming slides as well. And they impact how we apply AI as a technology in this space as well. It's clear that there is a lot of variation in healthcare availability, accessibility. There is a quality and trust variability. You encounter various kind of healthcare institutions. Of course, sanitization is being done. Back in 2001, there was a news report that 78% of doctors practicing in rural areas did not have any degrees at all, any medical qualifications at all. Of course, things have changed, have been improving further and further. There are improvements, but the variety of healthcare availability is very, very varied in the country. Of course, we are aware there is a huge shortage of healthcare professionals. Numbers have been improving. recommended levels are 1 doctor or 1 medical professional per 1,000 people, or at least not. It's a minimum recommended level by WHO, but numbers in India vary from geography to geography. PHCs and CHCs, primary healthcare centers and community healthcare centers, which operate in outside the cities, often face staff shortages. Right? You're aware of that. And urban-rural divide, in that sense, is quite visible. Absenteeism is also a known fact there. So there are challenges of operating in this kind of an ecosystem. So where do we go from here? There are structural gaps with limited access, quality, and affordability. Can AI make an impact in such scenarios? Right? Let's have a look at what has been happening in the country across different domains. But before we jump into that, let's just put a little bit have a look at a macro view. This is the expenditure reported for the country on healthcare space, in healthcare, government expenditure, public spending as it's called. India still, compared to our neighboring countries, also spends quite a less amount in healthcare, even on per PPP basis, which is balanced with respect to respective economic expenses. Out-of-pocket expenses have been an interesting, well, it's a important reality to know in India. Still 40% of the expenses are out-of-pocket. Number has significantly reduced in the last 10 years. 10 years ago it was 70% or so. And that means that anytime a medical emergency happens, a lot of people still will undergo financial hardship and maybe end up in poverty as well. So, having said that, there is definitely a lot of opportunity. State governments have been spending quite a lot on the money in the healthcare system. Some data about how the expenses have been at the public health level have been increasing over the last few years. And that gives us some opportunity as well, that the out-of-pocket expenses can they be reduced with the help of AI-based technologies in some ways? Can the public health system be made more efficient with the help of providing suitable technologies to be deployed in public health system as well as in private systems as well? So let's take we had a macro look right now at the economic level, but let's look at a micro look going back to a CHC. CHC is a community health center, typically designed to serve a population of about 1 lakh and above. Expected to have 6 to 7 doctors, but that may or may not be true in many places. And this is the kit of equipment they're supposed to have. What do you see here? You see delivery kit, which is some mechanical equipment. The only electronic medical device which you see in this list, a X-ray unit, right, costing about 1 lakh or so. Of course, you would require other equipment as well. Even availability of ultrasound machines in such locations is very, very limited. Right? 10 to 15 lakh rupees is the expense on these machines, and many times government public expenditure is not enough to cover for these equipment to be available. As I said, in India, there have been multiple systems for healthcare provision. There are hospitals of various nature where some places you find hospital rooms which are having 5-star room-like services available for you. In other places, you have very, very difficult scenarios as well. But of course, there are lots of shining stars as well. For example, Narana Healthcare Systems, again, many of you might be aware of it, started by Dr. Devi Shetty definitely more than a decade ago. Started in Bangalore, but it's now a multi-city organization, had IPO recently, a few years ago. They started with vision of providing affordable cardiac care, and operational efficiency, system level efficiencies they brought in their organizations as well. And what are they doing today? Again, as an innovative organization, they have started a spin out in some sense of their organization called Atma. This is again, I think the image is not very visible, primarily tracking all the data going through their hospital networks for operational efficiency, which was there definitely a way to achieve affordability and quality care earlier. But here they are trying to utilize the data gathered from the hospital systems to generate insights on clinical pathways, what works best, what doesn't work best. The data is gathered and the AI tools are applied on top of it to actually generate these insights and make decisions in their workflows. Similarly, another shining example is IISc hospitals. This is again more than 40, nearly 50 years old organization. Started with a goal of providing or preventing needless blindness in the country, and started by Dr. V, as he's popularly known as. But how they have moved forward from their original model of providing services in a efficient manner, how have these things evolved? They of course worked on medical devices, created very affordable intraocular lens, which is now sold in multiple countries, exported from India. So a huge improvement in eye care availability. But what are they doing now? They're also looking at how AI can help them to help make these decisions faster. Right? They're using AI tools with the help of a camera, which takes the image of the fundus of the eye, and glaucoma detection has been pioneered by them, along working together with Google as well as other startups from Bangalore ecosystem itself. Just want to touch upon a work we have been doing a little bit from the institute. Again, the results are not in the public domain yet, but something which is going on here with the support of ICMR in collaboration with St. John's Hospital. We have been looking at how do you improve access of ultrasound in remote areas. Right? Of course, ultrasound is a little bit complex topic because it has been misused for genital recognition as well. So there is a social impact of misuse of this technology by which leads to female feticide. So government has put in a lot of restrictions on how ultrasound can be used currently. So we are envisioning a different system here, how ultrasound can be provided with the help of new technology tools to be able to provide that in remote areas, yet having no access to the image at the site of use, but same clinical outcomes. How do we achieve that? But before we jump into that, some analysis we have been doing with the help of Dr. Gandhi and her team as well, looking at how ultrasound availability is currently there. Just an example of data analysis which is now possible. This is a map of ultrasound centers in Karnataka, distributed across different places. But the red dots in the urban areas and the green dots in the rural areas. If you count back in the back end, where these centers are, 92% of these centers exist in the urban areas, which cater to only 40% of the population. Right? The rest of the population which is sitting in rural areas has to migrate to these centers to actually get their ultrasound scans done. So every time you have pregnancy, you're expected to have 4 times ultrasound scans done, at least during that, if everything is normal. But for those access, you need to travel to cities to actually do that. So we're looking at how migration happens in this scenario as well. But just a caution in terms of blindly following data analysis. The students who worked on it, initially when they looked at how this map was generated, it was generated from data publicly available about addresses of PCB approved centers for ultrasound. And that map led to, but that was mapped onto using a Google's API to automatically locate these centers on a lat-long coordinate was obtained. But of course, if you don't do manual interventions, many of the centers, not that many, but a small fraction was sitting outside India, outside the state as well. Right? So they had to go back and validate that what the AI algorithm or the Google's APIs are doing, are they actually making sense or not? So they did some corrections back on that. So similar scenarios might occur in other places as well. Having clearly established the need, we have been looking into how to understand the ecosystem as well. So this is some work done earlier last year, looking at what do the stakeholders say. So that's a design-centric approach in some sense, looking at what the needs on the ground are so that technology developed is appropriate for use in that scenario as well. The system, or the proposed system, which was even before conducting this level of stakeholder engagement, was proposed like this. We have the ultrasound scanning being done in remote areas. Subsequently, the analysis is done at a remote site, a different site, and only a report is sent back, right? Now, this is sounds simple in that terms, but it's technologically challenging because when you're acquiring images, if you don't see the image, you can acquire wrong data, right? So we had to build specific technology to actually solve that problem as well, and that's some of the work which is going on in the back end as well. Of course, there's a cloud architecture for enabling that. The approach taken here is very much a user-centric approach. Sorry, some of the data has gone missing. But essentially, stakeholder engagement has been very much a central theme of this approach, right? Not only developing the initial prototypes, subsequent prototypes which are being developed are also being tested, or at least we are taking feedback from people. Of course, there are legal barriers in being able to take these prototypes to these locations and test them as well. So we at least take feedback from the users as we move along. Just one example of how the AI technology can help in this scenario. So for example, this is work done by my PhD student Pravalika. She recently presented this at a conference, but the key theme here is that once you're actually acquiring the data, you have to have a doctor to actually look at that image and then make a judgment whether the fetal growth is appropriate or not. Right? So in this case, she wanted to see whether we had tons of data when we are doing a ultrasound acquisition. From that, can I pick out the right image so that the doctor can take the decision faster? They don't have to spend too much of time for that purpose. So she developed some AI-based algorithm building on existing image analysis networks. So some of you who have used AI tools might be familiar with MobileNet, VGGNet. These are classical systems by which you can do image classification. She built a little bit on top of them to actually make it work for the fetal images as they're were required from our system, and got very good results in terms of accuracy and precision, reaching almost 100% in some cases. Right? Of course, this is a very limited data set acquired from phantoms. We had to actually do this work with the help of clinical data sets as well, and for our own scenarios as well. So that validation is still pending. Just to kind of wind up on that, I want to show this implementation of this system on a real-time basis. So it's data being acquired. This is not a real patient. This is only a phantom, which mimics the fetus. The data is probably not visible there, but it's in the real time being able to assess whether the head is being scanned or not, or some other organ is being scanned. Right now it's limited to the head detection. Because we're doing scan blindly, we want to make sure when we acquire the data in a blind manner, the data captures all the organs. So we want to extend that to all the organs detection and give a go-ahead that yes, the data capture is sufficient now. We can take this data offline, send it to a radiologist to make those assessments as well. So having said that, the goal is clear that we are looking to make access possible, enabling that through all kind of technology tools, AI being an important one there because we can possibly do better things with that. Ultimately, what we're looking for is improving access, improving affordability, and that's the goal of health technology pathways as well. In the workshop, we'll learn about all the other complications as well, which arise because we had to do the assessment. So final few point I wanted to bring forward was that regulatory system is also changing in this space. I think there might be a more detailed discussion later on, but just wanted to bring forward that India is coming late into this game compared to the other countries. We have Professor Sai already mentioned about regulatory approvals being in place, or regulatory structures being in place in many countries, and STA systems being in place in many countries. In India, this activity started. Drafts have been there in government proposals since 2006. I have been tracking them since that. But the actual rules were put into place in 2017 and became effective in 2018. And still, multiple years after that also, the implementation is kind of step-by-step progressing. So, many devices, including ultrasound devices, are now fully regulated. What's happening in AI space? Something to keep an eye on. AI is again a development on top of existing medical technologies as well. We have had multiple technologies which are usable in clinical space. For example, what's called a clinical decision support system. It's a software algorithm which tells doctors what decision to take, right, based on the data they feed into that. Such systems are also regulated in other countries. In India, only recently, this is from October last year, guidance have been put in, still for public consultation, so the guidance is evolving. This is for medical device software. There are two varieties here as well. Software sitting inside a medical device, software in a medical device, SIMD, and software as a medical device. Both will come under purview of these regulations as well. And just last week, last week only, June 8th or 6th, 7th, January 8th or 7th, this notification also came where they are looking into regulating AI-based cancer detection as well. So again, because it's a software, it can fall into purview of the SAMD or SIMD framework, but AI specifically people have to look into, and those challenges, I guess, will be discussed in the workshop down the line as well. So in conclusion, I just wanted to say that AI is a means, not an end. The end goal, so to say, is to improve healthcare, make it accessible, affordable for the masses. And we have responsibility as technology people, as designers, as policymakers to make sure that we put it to right use. Hopefully, with that, we can make use of AI and other technology tools such that healthcare is ethical, affordable, and scalable for the country. That's where I'll stop. Just before I close, I just want to thank a lot of people who have contributed to the work in my lab, and of course, the organizers for inviting me. And thank you for patiently listening. Happy to take any questions if you have. Offline. So I think I use in my classes, if students don't ask questions, I ask them questions. I ask them some questions, yeah.
Is there a framework for adoption of AI? Like AI is a new technology, so to speak, if you can call it that. Like a lot of new technologies, organizations or healthcare organizations find it difficult to adopt because they are stuck with isolated legacy technology. When AI comes in, has there been a framework defined for adoption of AI in a very